Hello, hello, hello. Check, hello, hello. Check, hello. My testing 1 2 3. Hello, hello. Check, hello. Hello, check, hello. Check 1 2 3. Hello, hello.
चल जाएगा. हेलो 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 चेक. हेलो 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 हेलो. थोड़ा ऑडियो बढ़ाओ. कम है काफ़ी. हेलो
Hello, hello, hello. Check, hello, hello. Hello, check, hello, hello. My testing 1 2 3. Hello,
हेलो 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 चेक चेक. हेलो 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 हेलो
hello, hello, hello. Check, hello,
हेलो 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 हेलो
Hello, hello, hello. Check. Hello. My testing 1 2 3. Hello. Hello. Check. 1 2 3. Hello. Hello. Check.
Hello. Good afternoon, everyone. A lot of you are former students. Uh, so I will repeat few things which I discuss in class also. That in science and technology, I think the biggest fear is particularly students who do not have a background. They often fear the subject because of the technical nature of it. Literally, we are studying technology, so it has to be technical. And that often makes students fearful. I personally think that except very few areas, for example, once you do whatever subject you study in graduation, that will be a very specialized subject. And in that particular subject, maybe you have some benefit in prelims or mains examination. But UPSC syllabus is not specialized. UPSC syllabus is quite general. And they can ask questions from any of the areas. And in all of those areas, every other candidate is equally at the same pedestal, that you have to just have faith in your aptitude. So the only point I am trying to make here is that no matter how tough this topic may look like, or all the topics I'm going to discuss in today's class also, that some of them may look like very difficult, but the questions UPSC is going to ask, that will not be very difficult. And having just a basic level of understanding will be more than enough to answer those questions. So my goal here will be to make you acquainted with that you have a basic level of understanding of all the important news which has been there in last 1.5 year. So that is what I'm going to do. If you look at the nature of questions, there will be 2-3 types of questions. One, the most popular type of questions will be application-based question, that they will give you a technology and you are supposed to know their various applications. And they particularly choose those applications which are very niche and which may not seem very logical prima facie. Only a deeper analysis will perhaps tell you that this is also correct. First type of question. Second type of question will be a general question where there will be, you're supposed to have some basic understanding about something. You're also supposed to know its one major application. You are also supposed to know its some challenges, limitations, etc. The third type of question will be that they will pick up a random technology which is in news somewhere, covered in newspaper or in some magazine, and you are just supposed to know the meaning of that technology, what all it is about. That's it, nothing else. Those questions, if you do not know about it, and if you prima facie have no, as such you cannot comprehend the meaning of the words there, then those questions can be difficult. Often they will look factual. But if you do have some background, then it can help you. So again, that is why I'm telling you that in a very specific set of question, if you have a very specific set of skill which you acquired in your graduation, then in few 1 or 2 questions you can have some help. Apart from that, everybody is at the same pedestal, and I think everybody can do really well in this topic. You can expect about 10 questions, but in some years there have been 14 questions also. I don't think more than 14 questions will be asked from science and technology, but I do think that 10 to 14 is a good weightage. And I also think that out of those 10 to 14 questions, I do think that 80 to 90% of the questions are attemptable. I think everybody can attempt it. You just have to have faith in your aptitude. Okay, so let's start today's class. Although topic में आपका biotechnology से दे रखा है, but I will start with space technology. Biotechnology and health, we will do that together. जो biotechnology और health वाले जो topic हैं, there are some overlapping topics, तो हम साथ में करेंगे. So first we will discuss space technology, then we will discuss ICT, information and communication technology, and then we will discuss biotechnology and health and rest of the topic. A brief announcement before I start the topics, that if you have any question, ask questions, but there are many supporting staff here, they have mic, so ask question in mic so that students who are watching it online, they also get to know the question and accordingly they will know what the answer is. So often what happens is that I do not repeat question, aadat nahi hai aise. So because of that, students only hear the answer and they do not know what the question was. So if you have any question, use the mic. There are supporting staff who will be there. Anyways, let's start today's class. I particularly don't think that UPSC will repeat a question so soon. There was a question in mains examination on Chandrayaan 3, a 15-marker question. So I do not expect a question from, although this year was quite busy from the perspective of space technology. You had at least 2 major missions, Aditya mission and ExpoSat mission, apart from Chandrayaan 3. So I do think that all of these topics are important except Chandrayaan 3. There was a question there in mains examination, but nonetheless, based on hunch, we are not going to skip topics. So we are going to discuss this topic also. I will talk about some basic stuff about Chandrayaan 3 that all of us should be aware about. This was our 3rd attempt and successful attempt, by the way. So Chandrayaan 1, all of us know that Chandrayaan 1, we launched that in 2008. It remained active for about an year. It was only an orbiter mission. Orbiter mission means that it only orbits around an object which it has been launched to, compared to lander and rover, where a lander is going to land on the surface and rover is going to roam around on the surface. So Chandrayaan 1 was only an orbiter mission. It remained active for about an year, and despite the fact that it remained about only for a year, it did provide us a lot of information. That is also given in your material. It of course provided a 3-dimensional atlas, detected water in vapor form, also discovered water ice in North Polar region. This water ice is in fact one of the reasons why Chandrayaan 2 had such great ambitions. Confirmed ocean magma hypothesis, which simply is a hypothesis that even moon at one point of time was in a molten state and gradually it had solidified. So it confirmed that hypothesis. Detected X-ray signals during weak solar flares or new spinel-rich rocks. Not that important. The most important thing you need to remember about finding of Chandrayaan 1 is that it found water. It found evidences of water. Chandrayaan 2 it was more ambitious. Chandrayaan 2 also had a lander, it had a rover, it had an orbiter of course. The orbiter still remains active, but the lander and rover we could not safely or we could not land it softly. And because of that it crashed. So, and imagining it is quite easy because anything which is falling towards moon even though is not as heavy as Earth, it is quite heavy. So anything which is falling towards moon, it is going to accelerate vertically, first thing. And anything which is moving around moon, so imagine that you have an orbiter which is moving around moon, it has its own speed, and then from the orbiter, lander got ejected, falling towards moon, and because of moon gravity, it is going to accelerate vertically, and it already had its own horizontal velocity. So it had its own kinetic energy, and that kinetic energy is further going to increase because of the vertical motion, and that vertical motion is due to lunar gravity. So you need to control both of that speed. You need to control that horizontal speed, you need to control that vertical speed. If vertically falls down with very high speed, it is going to crash, but so does the horizontal motion. That if horizontally it falls, and falls with very high speed, it is going to topple around, and again it is going to crash. So a controlled maneuver was very important. This is where we failed in Chandrayaan 2. So orbiter still is active, it still is providing us a lot of data, but the lander and rover, that failed. But nonetheless, that orbiter has provided a lot of information, for example, hydroxyl radical, water signatures, argon-40, some minor elements like chromium or manganese on lunar surface. So again, we do not have to go into that detail about findings of Chandrayaan 2. We should know that Chandrayaan 2 was not completely successful. Anyways, based on that failure of lander and rover, we planned Chandrayaan 3. Now this also has 3 important modules, had 3 modules, lander, propulsion and rover. The purpose of propulsion module here was to carry the lander and rover to the moon. So we used LVM-3 rocket, which is our most powerful rocket. It was earlier known as GSLV-MK3. I think this is also an important information we should know. That GSLV-MK3, or now known as LVM-3, that is our most powerful rocket, and we used LVM-3 for that. But LVM-3 is not that powerful that it can find a lunar orbit in one go. So whenever it is going to launch something, it is going to launch something in an earthbound orbit. So it launched Chandrayaan 3 का जो पूरा ये तीनों part है, it launched all three of that in an earthbound orbit. And then with the help of the propulsion module, which had its own fuel, its own motor, we kept giving it a boost, we kept raising the orbit, and very far away, when it was very far away from Earth, we gave it a boost, and we started the lunarward motion, that motion towards moon. And again, we used that propulsion module to ensure that it finds a stable orbit around moon. Then we gradually came down on the lunar orbit. When we were about 100 kilometers around moon, then these two modules, lander module and rover was part of inside lander rover. These two started their descent. And at this point of time, we invested a lot into ensuring that this does not fail. And for example, the lander and rover, they were equipped with multiple sensors. Those sensors, unka goal ye tha that all the time they had to measure what is their altitude. Such type of sensor is called altimeter. आपको दिखेगा, आप इसरो की वेबसाइट पे आप जाओगे, you will find that जो हमारा lander module था, that was equipped with altimeter, which literally means that its goal was to measure altitude, that है कितने height पे है. It had two velocimeter. One velocimeter measures velocity. So one velocimeter to measure horizontal velocity, another to measure vertical velocity. And why this measurement was calculated or necessary? Because we had done everything first on a supercomputer. We have to simulate all of that on a supercomputer, that how all of that is going to go ahead. And we had a computer there as part of lunar module itself. That computer had everything pre-programmed, that at what point, at what altitude, at what velocity, it is going to generate a thrust in opposite direction so that it can reduce the speed. So the point I'm trying to make again here is that once the descent started, I hope that many of you are watching it live, once that descent started, then we were not manually controlling it. Everything was pre-programmed, and the computer of the lunar lander module was doing all of that. And the instructions were based on that what will be the altitude, what will be the velocity, and accordingly the instructions were pre-programmed that at this point of time a thruster is going to execute and it will try to reduce its motion. So if you remember, for example, if you were watching it live, just before landing also, you remember many times people clapped, and that clapping was for particularly that part, that whatever we had programmed, it was working properly. It had a camera, a live camera. That live camera was fed into this computer, and this computer now was equipped with a particular type of AI technology, which is called computer vision. I will talk about that जब हम AI discuss करेंगे. Computer vision AI takes visual input, processes that input, and makes a decision. So there was a live camera which was recording the landing site, and the computer has to figure out that if this landing site is safe or not. Or is it going to topple? If it lands here, is it going to topple? So it has to figure out then and there. And only then it is going to take the final decision that what is the safe landing site here. And even then, we had a fail-safe mechanism. Our ideal goal was that just before landing, the speed, both horizontal and vertical speed, is exactly 0. But even then, we had this mechanism that even if it is, let's say, for example, falls at about 3 meters per second, then also fine, it's not going to topple, it's not going to crash. So there were a lot of mechanisms which were part of lunar lander module, jiska goal ye tha to ensure that it safely lands, and it did land safely. When it did happen, India became the 4th country to do that. Now Japan has become the 5th country. That is also something you should know for prelims examination, that Japan recently has launched its module called SLIM. आप देखना मटेरियल में कहीं इसी में दे भी रखा है इसी टॉपिक में. So Japan has become the 5th country to achieve that. And before India, it was US, it was Russia, and it was China. These 3 countries already had successfully completed this soft landing maneuver on lunar surface. Anyways, and the last part of this entire discussion is that what was the objective of Chandrayaan 3 lander and rover module? And that is shown here. Again, this was precisely asked by UPSC in mains examination. You're supposed to name of all of the modules as well as their objective. So जो lander modules, where there was a module called Rambha, and this module was equipped with a type of instrument which I want you to know. Again, just remember this name in one line. This was developed by a scientist named Langmuir, hence the probe is called Langmuir probe. The purpose of Langmuir probe is to know that if in your surrounding charged particles are there. For example, if I have a Langmuir probe device, then I can figure out that what will be the, let's say, electron density around me. Right? Electrons, we cannot see that with our naked eyes, but there can be multiple electrons here, or in general there can be many charged particles around here, and we want to know about those charged particles, their concentration, all of those things, and we use Langmuir probe for that. So in one line, I think we should remember that the purpose of Langmuir probe is to know the concentration of charged particle. That is what the goal of Rambha was. The goal of CHASTE was to know the temperature profile, that how temperature decreases or increases with depth. The goal of ELSA was to know about seismic activity, that there can be lunar quakes, and if those lunar quakes are there, then what is their intensity, what is their source. We haven't figured out the source part, but the initial probe has provided that yes, there is some seismic activity. These two payloads, they both are spectroscopic instruments. Spectroscopy is an idea where we try to figure out the molecular composition of a sample based on its interaction with light. So these two were different type of instruments. Jinka goal ye tha that wherever the rover roamed around, it collected some sample and it did an in situ analysis. It analyzed that sample and it tried to figure out that what elements are part of that lunar surface. And I want to highlight this also. Propulsion module has been quite useful, and this is something which I do think again we should know, that for the first time ISRO has achieved an amazing thing, that propulsion module which we first sent from Earth to Moon, but that propulsion module still had, हमारा जो plan इस तरीके से था कि इसका पूरा fuel हम exhaust नहीं करेंगे, it still had some fuel left. We gave it a boost at a point of time where it can come out of the lunar orbit and again it can fall into Earth orbit. So as of now, that propulsion orbit is revolving around Earth, not around Moon. And this we have done it for the first time, that we can send something to Moon, not on the surface. We can send something on the lunar orbit and we can bring it back to an earthbound orbit. That in itself is quite amazing. But by the way, this also had a payload called SHAPE. The goal of that payload was to collect data about Earth from so far away. That what makes Earth habitable. We want to know that just there are a lot of compounds. If you do find organic compounds, then that of course always is a very good signature that there may be life on a particular planet. For example, you find methane or you find dimethyl sulfide, things like that. Then you get to know, you have a, at least you can say that there is a probability that there is life on that particular planet. So the goal of SHAPE payload was to, can we know about such type of gases or molecules from so far away? And if we can, then perhaps this knowledge can be useful when we will do exoplanet analysis. If ISRO does some exoplanet, planet not part of solar system, we are collecting some data from planet outside solar system, and we are trying to figure out that can life be possible there also. And this knowledge, that the data which we collected about Earth from so far away, that knowledge can be quite helpful in that. So propulsion module was not just carrying lander and rover, it had again a very important objective. The first one this, and the second one, that it allowed ISRO to demonstrate the capability that we can bring something back from lunar orbit to earthbound orbit. This can be quite good for our future plans where we do want to send some astronauts on Moon. For example, after Gaganyaan, the next logical step will be that we send some astronauts to Moon. And we need to ensure that we can bring that payload back to Earth. So I do think that these are some of the basic information about Chandrayaan-3 which we should be aware about. Some key findings of Chandrayaan-3. I don't think we need to go into this detail. CHASTE payload recorded 70 degrees Celsius. We have found multiple elements like aluminium, calcium, iron, chromium. thin plasma, जो Langmuir probe है, that has found a very thin plasma. If that plasma was very dense, then it would have basically adversely affected radio communication. But because that charged particle density is very thin, it means that radio waves can easily pass through moon. तो जो हमारा communication है, it can function well on lunar surface. That is the significance of this particular part. जो ILSA है, that has found evidence of seismic activity. Again, I don't think we need to go into such great detail that which payload has found exactly what. इतने detail में UPSC I don't think is going to ask question. We also find the characteristic of lunar soil. For example, till now we have not found any organic matter on lunar surface. We have found that soil is lumpy. It's not like dust, but it can become lumpy. So some of the characteristic of lunar soil we have found. One of the hope here was that because it landed near South Pole, Chandrayaan-3 landed very near to South Pole at the latitude of about 70 degree, not exactly at 90 degree, but about 70 degree, where sunlight is still present. At 90 degree, जो lunar South Pole है, that always remains in shadow, right? Because of lunar orientation. जो lunar South Pole है, that's quite an interesting place because it always remains in shadow, and the here assumption here is, and that's a very good assumption, that because of lack of exposure to sunlight, overall the characteristic of lunar South Pole has not changed in millions or billions of years for that matter. So if we do analyze lunar South Pole, then we can get to know about early moon, or for that matter, we do know that moon was formed out of Earth, so we can also get to know about early Earth or early solar system for that matter. So Chandrayaan-3 landed near South Pole. One of the goal, which till now we have not been able to find, that there is a hypothesis here that lunar South Pole is quite rich with water ice. Lot of ice is stored here, and that ice has two very important significance. The first significance is that presence of water in itself is very necessary for life as we know it. हमारे हिसाब से लाइफ के लिए पानी होना बहुत ज़रूरी है. बिना वाटर के we cannot imagine life. As far as we know, again, because our entire data is based on Earth. All of the organisms on planet Earth, they need water to survive. So presence of water immediately tells you the possibility of life, first thing. Second thing, that hydrogen of water can be a fuel. We do know that hydrogen is a great fuel. So if we have, let's say for example, some sort of electrolyzer, some energy source here, then we can extract that hydrogen, and that hydrogen can become a source of fuel. And that will be quite good, because in future if we do make moon as a base, where human beings have colonized moon, and they start a journey from moon, then you have a ready-made source of fuel available. So that is another reason why lunar South Pole is very interesting. And the third reason why moon in general is very interesting is that there can be many minerals which are not available on Earth, but on moon they may be in abundance. But there is one particular mineral I want to highlight here is an isotope of helium, the helium which we find on planet Earth, that is helium-4. Now helium-4 is an inert gas, it does not react at all, but helium-3 is quite unstable. And helium-3 जो है, that can be utilized for nuclear fusion. I am going to talk about nuclear fusion in coming modules, and helium-3 is a great source of fuel for nuclear fusion. And moon is a great source of helium-3, and the reason why there is so much of helium-3 might be on moon, because moon all the time is being bombarded by cosmic particles, by solar particles. Even Earth is getting bombarded, but Earth का जो पूरा atmosphere है, जो magnetic field है, that does not allow a lot of those particles to enter. So a lot of nuclear reaction is happening on the lunar surface, where hydrogen all the time is converting into helium-3. So that is a reason also scientists are so interested in exploring moon, that we can find a very good source of nuclear fusion based fuel on the lunar surface. Again, these two things we haven't found till now. So water, जो Chandrayaan-3 जो है, we haven't found that water ice, which is an hypothesis, and we also haven't found till now that traces of helium-3, which was a expectation. I don't think anything more than this is required in this particular topic. If you have any doubt, questions, you can ask. Let me explain the second topic. Second topic, why, first let me explain that why this topic is given. Tidal locking as a phenomena, why it has been talked about. जो lunar rotational velocity है and जो lunar revolution velocity है, both of them are same, right? So moon also rotates on its axis, very similar to Earth. Moon also has its own rotation, and moon also has its own revolution around Earth, and it also revolves around Earth. And one revolution or one rotation is 360 degree. So the time it takes for it to revolve and the time it takes for it to rotate in terms of rotational angular velocity, that is same. This particular phenomena is called tidal locking. And why tidal locking happens, that is quite interesting. Anyways, why this topic is covered, पहले तो ये डिस्कस कर लेते हैं. तो जो हमारा पूरा चंद्रयान 3 लैंडिंग है, हमने इस तरीके से अब प्लान किया था that the moment lunar day starts, Chandrayaan 3 is going to land. Chandrayaan 3 was powered by solar panels, and those solar panels require energy. So one moon को एक complete revolution होने में it takes about what, 28 days. So for 14 days you have light, sunlight, and for 14 days you have darkness. So our landing, it exactly matched with that starting of the lunar day. And once that lunar day ended, then it went into a sleep mode. But once an area does not receive sunlight, moon does not have any atmosphere, so all of that heat energy escapes into atmosphere, and moon becomes very cold very fast. The temperature can drop to minus 50, minus 60, minus 100 degrees Celsius very fast. At such low temperature, clearly all of the equipments are not going to function. And there is always a fear that those equipments will not function once they reawaken also. ISRO always knew that. ISRO knew that कि ये जो Chandrayaan 3 lander and rover है, उसका timeline 14 दिन का होगा. There was a hope that maybe we will be able to reawaken it once that lunar day again re-emerges. But that did not happen. Anyways, that we were prepared for it. हमारा ऐसे भी प्लान था कि 14 दिन तक हमारा जो लैंडर एंड रोवर एक्टिव रहेगा, उसके बाद इट इज़ गोइंग इनटू अ स्लीप मोड. इट इज़ गोइंग टू स्टे देयर. वी कॉल दैट पॉइंट नाउ शिव शक्ति पॉइंट. एनीवेज, बट व्हाई टाइडल लॉकिंग हैपेंस, दैट इज एन इंपॉर्टेंट क्वेश्चन, एंड दैट इज अ क्वेश्चन वी शुड आंसर, बिकॉज वी ऑफन रीड अ लॉट अबाउट टाइड in geography, but we do not understand the concept of tidal forces very well. The concept of tidal force is quite simple, that when we describe gravitational force, then we often make quite simplification. For example, that if something is falling on Earth, let's imagine that there is a large stick of length L which is falling on Earth vertically, not horizontally. In my thought experiment, I'm assuming that there is a large stick which is falling on Earth vertically, not horizontally. So if it is falling vertically, then the distance of this part of this stick and this part of this stick, that is clearly not same. If this is h1 and this is h2, then what it means is that the part of stick which is closer to Earth is going to feel more gravitational force, and the part which is farther away from Earth, that is going to feel less gravitational force. Now Earth का जो पूरा diameter है, that is जो radius है, that is 6400 kilometer, and ये stick मान लो अगर ये 5, 10, 100 kilometer का भी हो, तब भी in front of 6400 kilometer, 100 kilometer is quite less, so we can neglect it. And in general, in our day-to-day life, we do not encounter a 100 kilometer long stick. But imagine a situation where I have a 1000 kilometer long stick, and that is falling vertically towards Earth. Now for 1000 km long stick, now this difference cannot be neglected. What it means is that this particular part of this stick is going to experience a much stronger pull compared to this particular part, right? And that is going to create a tension within that stick itself, that one part is being pulled much faster, another part is being pulled much slower. And that difference in gravity because of size, that is what tidal force is all about. So the first thing we should appreciate, that whenever I'm using the word tidal force, it simply means that we are talking about an extended object, and that extended object is feeling gravitational force because of another object. But that extended object, some part of that is going to feel more gravity compared to the part which is farther away from the other heavier object. That difference is what tidal force is all about. So ये सबसे पहली चीज़ clear होनी चाहिए, and we can now use this concept in astronomy in general. जैसे in case of black holes, scientists use a phenomena called tidal disruption event. And in tidal disruption event, what happens is that a black hole can feed on a star, a nearby star can become part of a black hole very fast. But imagine the part of the star which is closer to the black hole and the part of the star which is very far away from black hole, and stars are extended object without a doubt. So the part of the star which is closer to the black hole, it is going to fall much faster, and the part which is farther away is going to fall relatively slower. So black hole literally rips apart that star. It rips apart in its slices. And this particular phenomena, often scientists describe it as a tidal disruption event. Again, why it is happening? Because the part of the star closer to black hole experienced much stronger force. Hence the word tidal disruption event. So tidal disruption event has nothing to do with any type of tide which we see on Earth. We are talking in the case of black hole eating a star. This particular phenomena is also called spaghettification, because that star gets ripped apart like a spaghetti. Spaghetti is an Italian dish, looks like noodle basically, samajh lo, that it gets ripped apart like a noodle. So because of that, it is called spaghettification or tidal disruption event. So tidal forces always will occur if there is an extended object, and because of that extended object you have that difference in gravity. So imagine now Earth and Moon. The part of Earth which is exposed to Moon, that part is going to experience much more stronger gravity, and the part which is not farther away from Moon, that is going to experience less gravity. Now the thing about Earth is that 70% of that it is ocean, and liquids can change their shape much more easily. Solids के लिए ज़्यादा मुश्किल है, but liquid के लिए बहुत ज़्यादा easy है. So this leads to a bulge-like situation. And what you describe as a high tide and low tide, that is from our perspective. But think about it, if somebody sees this from outside, then from that outside perspective, that bulge is all the time it is there. The only thing is that you are rotating inside this bulge, and whenever you come across this part, you experience high tide, and whenever you come to this part, you experience low tide. But that always is there. The tidal bulge is always there. You are just rotating inside that tidal bulge. So we can explain the concept of tide, which occurs on Earth in oceans, with the help of lunar gravity. But Moon का जो impact on Earth, that is much smaller, because Moon is a much smaller object compared to Earth. जो Earth का impact on Moon, that is much more stronger. Now Moon is solid object. Moon does not have those oceans. It is solid object, but even solid object, they do get stretched. So because of that, the earlier Moon, it got stretched like this. It did not remain a spherical object. Whenever it was formed, it did not remain a spherical object. But remember, it is still rotating. So there is a gravitational pull because of Earth, but it is rotating, and that rotational axis and that gravity is not aligned here. And that causes an opposite torque here. Torque is when we use in case of rotational motion. Whenever we think of something going in a straight line or in a circle, we use the concept of force. But whenever something is rotating, we use the concept of torque. For example, if I have to open this door, the door handle is at the end. If that door handle is where the door hinges, opening the door will be much more difficult, even if I apply the same force. So imagine this is a door, and there is a door handle which is here. It makes sense to have door handle here, Because if I have a door handle here and if I apply the same force, it will be more difficult to open the door. So the parameter which measures the distance along with force together, that parameter is called torque. And whenever we talk about rotational motion, we have to talk about torque. We do not talk about force, we talk about torque. So in this case, the tidal force का जो difference है, and जो gravitational pull and tidal force के बीच में एक some sort of समझ लो एक tug of war चल रहा है, and because of that tug of war you have a torque here, you have a net torque, and that net torque is going to reduce the speed of moon. And as the speed of moon reduces, it is going to match up with its overall revolution velocity. It can be mathematically shown, I will not go into that detail, that this tug of war will occur till the point of time that the moon's rotational velocity and moon's revolution velocity, both of them match each other. If that matches, then we say that it is tidally locked. And because it is tidally locked, now you are only going to see one part of the moon. And let me show that with a animation, that what it will look like. I was talking about Chandrayaan-3, the orbital raising. Okay, this is what I'm talking about. That there are two scenarios. In the first scenario, the moon is tidally locked, which by the way it is as of now. And look at the smiley face always towards Earth. And in the second scenario, when it is not tidally locked, what it was perhaps originally when it was formed, then we do not see the same face. We see all of the face of the moon. We do not see only one face of the moon. But as it gets tidally locked, that is, its rotation and revolution matches each other, then it gets tidally locked and we only see one face, one part of the moon. The other part which we cannot see, we call that dark side of the moon. It has nothing to do with if it receives sunlight or not. That other part also receives sunlight. Because we cannot see it, we call it dark side of the moon. So just remember that also as a fact, that this dark side of the moon is nothing but the other part of moon which we cannot see. And why we cannot see? Because moon is tidally locked to earth. अगर मान लो अर्थ एंड मून करीब करीब सेम साइज के होते तो अब तक अर्थ भी टाइडली लॉक्ड हो गया होता मून से. That is also there. In fact, in few billion years it is going to happen. That earth will also be tidally locked in few billion years. Meanwhile, earth will not be there in few billion years. You ask a question that why Mercury is not tidally locked to sun. By the way, Mercury is not tidally locked to sun. You should know that. उसका कारण ये है कि there is a Venus. And Venus, even though it is a very smaller object, it is much closer also. And that Venus का जो impact है, that is in the opposite direction compared to sun. So that is why Mercury is not tidally locked to sun. But all objects, because of gravity, given the enough time, few billion, few trillion years, they will be tidally locked to each other. In fact, the tidal disruption also occurs in case of planet and its moon. अगर moon बहुत पास में होता अर्थ के, then earth would have shed it apart. Even though it is solid, even if it has become solid, the part of moon which is closer, the part of moon which is farther, there would be a tension there. And earth would have ripped apart the moon in many, many pieces. So it is possible if the moon was very closer to the earth, but it is not closer and it is safe, it is in the safe distance. And because of that, it is tidally locked but not been ripped apart by earth's tidal force event. So this entire concept, why we are discussing this entire concept, the reason is quite simple. Because हमारा जो पूरा plan इस तरीके से था कि जैसे ही lunar day शुरू होगा, we are going to have Chandrayaan-3 landing. हमारा goal भी यही था that it is going to remain active for one lunar day, which is about 14 days. And we knew that there is a very good chance, very high chance that after one lunar day it is not going to be active, and that is exactly what happened. There was a hope that maybe we will be able to revive it. So this is what tidal force is, or how that bulge in case of earth and moon, how that rotation is going to slow down. So in this entire topic, I just want you to know 2-3 simple concepts. You should know lunar day. Lunar day का time क्या है, and now you know lunar day का time क्यों होगा 14 दिन. वो 14 या 14.3 जो भी हो, वो क्यों होगा. Now you know that. And why tidal locking happens? It's simply because of the differential effect on moon by Earth's gravitational force. And I will repeat this, even Earth experiences that. And because of that, we experience tide. But will Earth be slowed down because of lunar tidal locking? Given the enough time, maybe yes. But that time, if you calculate, that comes out to be in billions of years. And moon already is going few centimeters away from Earth. So tidal locking का जो event, जो पूरा impact है, that further is declining. That further is going to reduce as moon becomes farther and farther away. But even two objects can get tidally locked to each other. That means that both of them are going to see only one part. So if you are on moon, then you only see half of the Earth. You never see the other half of the Earth. As of now, that is not going to happen because Earth is not tidally locked to moon. If you have any doubt here in this topic, you can ask, yes.
सर एक्चुअली जैसे अभी आपने कहा कि हमने साउथ पोल पे लैंड किया था जहाँ पे हमेशा ही अंधेरा रहता है.
साउथ पोल के नियर लैंड किया था. आई विल से कि साउथ पोल पे नहीं, 70 डिग्री पे हमने लैंड किया, 90 डिग्री पे नहीं. एनीवेज कंटिन्यू योर क्वेश्चन.
वहाँ पे लाइट होती है ना?
वहाँ पे लाइट होती है
जी, बस ठीक है सर.
हाँ हाँ 70 डिग्री पे लाइट होती है. अगर लाइट नहीं होती तो फिर सोलर पैनल भी जो हमारा लूनर लैंडर का जो वर्किंग था, इट वाज नॉट बेस्ड ऑन सम प्री चार्ज्ड बैटरी, इट वाज नॉट बेस्ड ऑन सम न्यूक्लियर बैटरी, इट वाज बेस्ड ऑन सनलाइट. सो दैट इज व्हाई वी डिड नॉट लैंड ऑन 90 डिग्री. एंड यू आर राइट, अगर हम 90 डिग्री पे करते तो हमको सनलाइट नहीं मिलता
जी.
तो हमको कुछ और मैकेनिज्म यूज करना पड़ता. एनी अदर क्वेश्चन? यस.
So is tidal disruption the reason why Saturn has the rings around it due to fragmentation of moons and all?
Sorry, can you?
Is tidal disruption the reason behind why Saturn has rings around it?
Not at all. The question is that is tidal disruption the reason why Saturn has ring around it? Saturn का जो ring है, that is primordial rings. That when solar system was formed, along with sun, many other planets were formed. That has to do with how stars get formed. You have a lot of cosmic dust accumulating together. That cosmic dust, as it becomes huge, it becomes a star, but a lot of that also becomes all of those smaller objects which we call planets. Planets start revolving, they find a stable orbit, they start revolving. But not all of that will become planets. Some can become smaller fragments also, asteroids, or even those rings of Saturn, right? So tidal disruption event is not behind the rings of Saturn, yes.
हेलो सर.
You have to, हाँ जी, go ahead.
सर जैसे आप बोले कि मून का जो रोटेशनल टाइम है और रिवोल्यूशन टाइम बहुत अरसे हैं, तो हमारे सोलर सिस्टम में ये ओनली सेलेस्टियल ऑब्जेक्ट है या इसके अलावा भी कोई और ऐसा
जो टाइडली लॉक्ड है?
हाँ.
क्वेश्चन ये है कि सोलर सिस्टम में अर्थ एंड मून के अलावा और भी ऑब्जेक्ट्स हैं क्या विच आर टाइडली लॉक्ड? आई डू नॉट नो, बट आई डू थिंक दैट सम मून्स ऑफ जुपिटर शुड बी टाइडली लॉक्ड टू जुपिटर. ये कंफर्म करना पड़ेगा मुझे. But if I have to make a guess, then the best guess will be that at least some, if not all, at least some moons of Jupiter, and Jupiter has many by the way, Saturn also has many moons, so at least some of them should be tidally locked to their respective planet. But I will have to confirm, so I will not say that with high 100% surety. आप इसको एक बार confirm कर लेना, right? But the best candidate that why Mercury is not tidally locked, तो उसका कारण जो है Venus है. हाँ, you had a question, इनको mic दीजिएगा.
Why the Earth is not tidally locked with the Sun?
Because Earth is, again, that's a very good question, that why Earth is not tidally locked. Earth is very far away. Earth is 150 million kilometer away from Earth, Sun. So the tidal impact, even though Sun is a huge object, but 150 million kilometer is average value. 150 में आप minus 6400 करो, that is one part of Earth, plus 6400 करो, that is another part of the Earth. 150 मिलियन में आप 6000 किलोमीटर आप ऐड करोगे तब भी जो इम्पैक्ट होगा वो नेग्लिजिबल होगा. सो अगेन गिवन द इनफ टाइम, इवन अर्थ गेट्स टाइडली लॉक्ड टू सन, बट दैट इनफ टाइम विल बी नॉट इन बिलियंस इन ट्रिलियंस ऑफ ईयर्स. तब तक सन भी नहीं रहेगा. सो बट द पॉइंट इज दैट व्हाई अर्थ इज नॉट टाइडली लॉक्ड टू सन, सिंपली बिकॉज इट इज वेरी वेरी फार अवे.
Okay, sir. Then what will happen if Earth?
If Earth is tidally locked to Sun, what will happen is that one part of Earth will not be at all habitable, and the other part will also not be habitable. Both of the part of Earth will not be habitable simply because one part will be very very hot all the time, another part will be very very cold all the time.
Okay.
Simple.
Thank you.
सर मेरा को
ये क्वेश्चन है कि जो जो ये कॉन्सेप्ट है टाइडल लॉकिंग का, इसके तहत आपने बताया है कि जो मून का एक फेस है वही
हमेशा देखते हैं हम।
अर्थ की तरफ रहता है सर। तो फिर जो मून का साउथ पोल है जो सन की तरफ कभी भी एक्सपोज नहीं होता है ना,
नहीं, अब ये दो अलग अलग कॉन्सेप्ट
मून का जो साउथ, इसके लिए मुझे रीजन जानना है। मून का साउथ पोल वो,
अब ये दो अलग अलग चीजें होंगी। तो पहले तो व्हेन आई एम सेइंग दैट वन पार्ट ऑफ मून, इमेजिन दिस टू बी अ मून, when I'm saying that one part of moon is exposed, then I'm talking about this part. That has nothing to do with north and south pole. So ये जो part है यहाँ पे अभी भी sunlight आ रहा है. I'm imagining that this is moon. So one other part is also receiving sunlight, right? But this part we call it dark side of the moon because we do not see it. The reason why, so for example, you answer the question why we have a 6-month day and night on poles. ये पढ़ा है ना आपने? That poles पे 6 month day and night है. That has to do with the axial tilt of Earth's rotation, and same axial tilt is little bit more in case of moon, and that is why you have all the time darkness there. So that has nothing to do with tidal locking, that has to do with that what is the axial tilt of lunar rotation. I think we have spent enough time in this topic. Let's go to the next topic, which according to me is one of the most important topic to be asked by UPSC. So I'm going to spend a lot of time in Aditya L1 mission here. I do expect at least one question from this topic in prelims, and if not in prelims, definitely in mains examination. So two things, I'm going to divide that into two parts. First, we will talk about its objectives, and second, we will talk about L1, what does that L1 signify, and I expect I can frame multiple types of question. यहाँ पे UPSC के पास कोई डार्थ नहीं है themes का, कि किस टाइप का क्वेश्चन यहाँ से, they will not even ask a question on Aditya L1, they can ask a question from sun itself. They can ask the question about layers of sun. So I'm going to discuss all of that one by one, starting with first few of the basic aspects of sun. Forget about Aditya L1 mission. But first try to, what we know about sun till now, let's at least try to have that information. That sun has a core, that core has temperature of about 15 to 20 million degrees Celsius. At such high temperature, hydrogen nuclei can fuse together, can form helium, which is what nuclear fusion is. And in nuclear fusion, lot of energy is emitted. So that is the first thing, that in the core of sun, nuclear fusion is happening. You can think of this as a furnace, and that furnace is heating up the entire star. In fact, that is the mechanism which happens inside all of the stars. That you have a furnace, which is quite a small furnace, given the fact that stars are really huge. But a small furnace, but produces so much of energy, that entire star is so hot. The core temperature is 15 to 20 million. You have radiative zone, you have convective zone. I'm not interested in that part. I'm interested in the three outermost layers, because that is what Aditya L1 is going to discuss. The part of sun which you see with your naked eye, never do that. But whatever you see with sun naked eye, that part is called photosphere. That is where all the light which is getting emanated by the surface, and we get to see that part. Thankfully, we are very far away. Otherwise, sun is so bright that it would have immediately blinded us. But since we are very far away, we can see at least indirectly of sun, or we can take a picture of sun from multiple type of optical instruments. And beyond photosphere, you have a very small thin layer which is called chromosphere, which is little bit, again उसका temperature vary करता है, बहुत ही thin layer है, naked eye से नहीं दिखेगा आपको, but with very good optical equipments you can see that photosphere के beyond there is a thin dynamic layer which is called chromosphere. And the most interesting layer is the outermost layer, which we call corona, shown here in this particular animation. That corona जो है, जो sun का जो average temperature है surface का, that is about 6000 Kelvin. The core is 15 to 20 million Kelvin, and the temperature drops to 6000 Kelvin on the surface. Again, 6000 still is quite hot for us. For example, for our reference, the hottest part is the core of Earth, and core of Earth is at 6000 degrees Celsius. But यहाँ पे जो सबसे coldest part of sun है, that is the surface, and that is 6000 degrees Celsius. So again, hot and cold are relative. So जो photosphere है, that is at 6000 degrees Celsius. The temperature drops little bit in chromosphere. or can increase also. Chromosphere is a dynamic layer. But corona, that is where temperature can go up to 2-3 million degrees Celsius also. And again, this remains one of those things where we do have theories, but we do not have really good theories. We do not have really good explanation of that coronal heating mechanism. That a corona jo heat up hota hai, that suddenly temperature goes up to few million degrees Celsius. Then why is it so? The obvious question you ask is that if corona is so heated up, it should emit lot of energy, electromagnetic wave, and we should be able to see that energy. The problem is that corona is also a very scanty region. जो coronal density है वो बहुत ही कम है. कोरोना के जो particles हैं, they are separated very far away from each other. So individual particle का energy बहुत ज़्यादा है, but total number of particle बहुत कम है. So because of that, the energy is not enough that we can see that with our naked eyes. And photosphere, even though temperature is so less, it is so dense, and the energy density is so high that we can see photosphere with our naked eyes. Only during total solar eclipse, where the entire sun is covered by moon. Now moon and sun, they look the same, because even though moon is 10 times smaller, it is also 10 times nearer to us. So they look the same in the sky, and moon can have this shadow over sun, and in that case you can see that corona. So corona becomes visible during total solar eclipse, because the light of photosphere hai, that gets blocked. That is the first thing about sun, its various layers. I want you to remember the 3 layers here. The first is photosphere, the layer which we see. Second is chromosphere, and third is corona. The second thing which I want you to know is that not everything which comes out of this sun is useful for us, and not everything which comes out of this sun is the visible light which we can see with our naked eyes. We only see a very small fraction of light, and we call it visible light because in our perspective it is visible. During some specific events, sun can emit light ranging from X-ray, ultraviolet light, visible light, up to radio. That particular event, a very explosive event, is called solar flare, which is shown in this picture. Solar flare, there are 3 words which are used a lot interchangeably, but all 3 of them are 3 different things, and that is, I generally would have not gone into this detail, but because Aditya L1 mission aims to know all 3 of them separately, so we should know how 3 of them are different from each other. So the first event is called solar flare. Solar flare is essentially light, but light which is very bright. It has very bright energy, and most of that light is not visible, by the way. Most of that light is X-ray or ultraviolet light, which we cannot even see. That even though we cannot see it, but that light's brightness intensity is very high. And compared to one solar flare event, in this particular animation, you can see the size of Earth. So compared to Earth size, you can think of how big a solar flare event is. If you are near to solar flare, the entire Earth gets vaporized immediately. But thankfully, we are not near to sun. Now, sun and Earth ka jo average distance hai, it is 150 million kilometer. And because of that, after all, that solar flare is nothing but light, and light travels with 3 lakh kilometers per second. So it is going to take about 8 minutes for that solar flare. So whenever a solar flare event happens, sun already is so bright that हमारे eyes को फर्क नहीं पड़ेगा. But if we have a very powerful telescope, that telescope can resolve that it has recorded a solar flare event. One solar flare event can be brighter than thousands of atomic bombs together. So think of 1,000 atomic bombs being exploded together, and solar flare will be brighter than that. So solar flare essentially is light, but not just visible light. In fact, most of that is X-ray, ultraviolet light, and even visible light or infrared or even radio wave is part of it. But most of that, it is X-ray and UV light. That is solar flare. And then there is another event which is called coronal mass ejection. Again, these 2 are used interchangeably. Solar flare and coronal mass ejection are used interchangeably, but they 2 are 2 different things. They 2 happen together most of the time, and because of that, people use it together. But these 2 are 2 different things. Coronal mass ejection essentially is plasma. We are talking about charged particles. We are talking about electrons, protons, hydrogen ions. Charged particle, but their concentration is very, very high. From one part of this Earth, billions of tons of plasma is getting released into outer space, and some of that can reach towards Earth also. So coronal mass ejection is not light, it is particles. It is either electron, it is proton, hydrogen ions, it is essentially particle. And particles cannot travel with speed of light. Particles can come very close to speed of light, but they can never travel with speed of light. So coronal mass ejection event will take few hours, even a day or two, to reach to Earth, right? I often use this, the difference between when you, let's say for example, imagine a cannonball, and imagine a cannonball being fired with gunpowder. So imagine that when you are burning that gunpowder, that is what solar flare is. That gunpowder, when it burns, it is going to create a flash of light. But think of that cannon which comes out of that cannonball, that will be very directed, and of course it will be not that fast. जो bright light है, light travels with very high speed. But think of that cannonball as that coronal mass ejection. But if you are in path of that cannonball, then it can cause lot of damage. If that cannonball misses you, then it can cause no damage. But towards path, it can cause lot of damage. So that is what coronal mass ejection is. That पूरा जो space है बहुत huge है, and if Earth somehow unfortunately comes in the total intensity, maximum intensity of coronal mass ejection on its way, then that is quite bad. And how it is quite bad, I am going to explain that. But first I want you to distinguish between these two phenomena, solar flare, coronal mass ejection. And then there is a third event. The third event is called solar wind. So solar wind is all the time charged particles come out from sun. From time to time their concentration increases. But इसका जो overall prevalence है, वो बहुत ज़्यादा recurring phenomena है. जो solar wind है, वो recurring phenomena है. जो solar flare या coronal mass ejection है, वो rare phenomena है. That will happen sporadically. Solar wind is going to happen all the time. But even solar wind is nothing but charged particles. Solar wind is not light. Solar wind is charged particles. These are electrons, protons, hydrogen ions. These are, we are not talking about light here. So I will further again repeat the difference between these three things. Solar wind is stream of charged particles which come out of the sun all the time. Second, solar flare, that essentially is very high energy light, ultraviolet light, X-ray, visible or infrared also, but very bright light. And third, coronal mass ejection is again charged particle, but now we are talking about billions of tons of plasma together. Charged particle, but उनका जो energy है और जो density है वो बहुत ज़्यादा है. And all three of them can have three differing type of impact. For example, let's first understand impact of solar wind. That is the simplest thing. Turns out that Earth is a very powerful magnet also, and Earth का जो magnetic field that extends millions of kilometers into sky. That magnetic field, it creates some sort of a shield against that incoming charged particle. It does not allow all of those charged particles to enter inside atmosphere. A lot of those charged particles, they get repelled by Earth's magnetic field. That also leads to formation of what we call geotail. Geotail is a part of ये जो पूरा Earth का जो magnetic field का shape है. Again, by the way, this is a 2D picture, but the actual scenario which we cannot see, of course, with our naked eyes. But if you draw this magnetic field, then you cannot draw that on a piece of paper. You will need a 3D. It is a 3D magnetic field. So this entire shape is called magnetosphere. जो Earth का जो पूरा magnetosphere है, that is like a shield for all that incoming particle. And lot of these incoming particles, they will be simply repelled. But this interaction also leads to this extension of Earth's magnetic field, which is facing away from the sun. And this particular shape is called geotail. Just one line, geotail का मतलब क्या है? Geotail is basically a particular part of Earth's magnetic field which is facing away from the sun. एक line में I'm just defining geotail, that it is nothing but a part of Earth's magnetic field which is facing away from Earth. And that essentially is because of that solar wind. Anyways, this entire interaction of particles in Earth's atmosphere because of Earth's magnetic field, there is a name for it. That name is called geomagnetic storm. Geo means earth, and magnetic here means that this storm or whatever is happening, that is essentially because of earth's magnetic field. Now ये geomagnetic storm का impact कितना strong होगा, ये इस बात पे depend करता है कि जो solar particles का energy है और जो solar coronal mass ejection है या solar wind है वो कितना strong है. In its most simplest form, by the way, from some areas these particles can enter. This particular area is called polar cusp. And when these highly charged particles interact with outer atmosphere of Earth in the polar areas, they produce beautiful light. We call them aurora, right? Aurora australis or borealis. Looks like, which may look like this. People often book expensive tickets to go to Arctic or Antarctic to see aurora, right? So as long as it is aurora, it's fine that you get to see the entire sky shimmering with this beautiful light. But if that geomagnetic storm is very powerful, that is no longer those particles are entering only in polar areas, they are entering into other latitudes also. So the second thing which can happen is that we can witness aurora in other latitudes also. If it is even more powerful, then it can disrupt the radio communication, the GPS satellite. If it is even more powerful, then it can also disrupt your power transmission line. जो पूरा आपका power infrastructure है, that gets disrupted because of a sudden magnetic activity, and changing magnetic activity produces electric field. And that electric field will lead to surge of electricity in the wires, and our electric grids are not made for very high surge in electricity. It can cause a blackout, and that blackout will not be localized, it can become a global blackout. A larger part of Earth can witness a blackout. So geomagnetic storm का impact क्या होगा, ये इस बात पे depend करता है कि how much wrath of coronal mass ejection we are facing. That what is the density of that coronal mass ejection which we are facing. Even solar flare can cause a lot of changes. Solar flare basically means that suddenly you have a very bright light, and we do know that light can interact with atmospheric particles. Suddenly in atmosphere you have particles which have lot of energy, and those particles can be charged. So even though solar flare is not charged particle, but it can give more energy to charged particles in the atmosphere, and that can also disrupt radio communication, or it can increase or decrease the atmospheric drag, which can change the orbit of satellites also. So solar flare also has impact on Earth. Some impact can be similar. For example, those charged particles in the atmosphere, they can also cause aurora. But some impact is very specific to coronal mass ejection. जैसे जो disruption of power grid वगैरह है, that often will occur because of coronal mass ejection. The reason people use these two together, because often both of them happen together. And people get confused also. जैसे UPSC ने question पूछा था that what will be the impact of solar flare? And उसमें एक option वो भी था कि power grids will be lost. And जो कि मुझे I knew that answer उसका सही होगा. But अगर आप technicality में चले जाओ, then वो statement गलत है वो. That solar flare per se only cannot cause disruption of power grid loss. That will be done by coronal mass ejection. So anyways, these three are three different things, and they can have their own impact. Solar wind maximum will cause aurora, nothing else. Coronal mass ejection can cause multiple things. Failure of communication satellite, GPS satellite, changing orbit of satellites, power disruption on Earth, auroras across various latitude, and even solar flare can cause lot of these things, if not all of them. So that is second thing which we should know, that sun के layers के अलावा जो sun से associated events हैं वो क्या क्या हैं. And third thing, before I enter into Aditya mission, third thing which you should know, two concepts associated with sun again. The first is concept of sunspots, and second is concept of coronal hole. And these two concepts, they both are directly, जैसे particular जो sunspot का concept है, that directly is associated with solar flare and coronal mass ejection. We do find, again, we do not know why it happens, but we do know what happens. What we do find, that when we look at sun with the help of telescopes which are looking at sun in visible light or even infrared light, then we do see that there are part of sun जहाँ पे जो thermal emission है बहुत कम है, which basically means that यहाँ पे जो temperature है कम है. Surrounding का temperature बहुत ज़्यादा है. For example, if the temperature here is 6000 Kelvin, maybe here temperature is 4000 Kelvin or even 3000 Kelvin. So again, high-low is relative. So we find that sunspots का जो temperature है compared to surrounding, that is very less. But we also find that यहाँ पे जो magnetic field है वो बहुत twisted है. जो magnetic field है, it is very strong and it is very twisted. And it does not allow lot of highly energetic particles from the bottom of the sun to come on the top. And in fact, these two are interconnected. The twisted magnetic field, you can think of this like as a squeezed rubber, that you have squeezed a rubber which is not allowing it to regain its natural shape. So in all the sunspots, the magnetic field is so twisted and so strong that it does not allow high energetic particles to come on the surface. But from time to time that magnetic field realigns, and whenever does that happen, you have suddenly energetic particles coming in millions and billions of ton, and that can cause solar flare or coronal mass ejection. So the sunspots का जो concept है, that is directly associated with the phenomena of solar flare and coronal mass ejection. And we also see that these sunspots occur in a cyclical manner, that you have a 11-year cycle, जहाँ पे, अच्छा by the way, sunspot randomly कहीं पे दिखेंगे आपको, they will expand into area, and then they gradually will also start reducing. So when their area is maximum, then this maximum area, and after that again it decreases, again goes back to maximum. So one maximum to another maximum, it happens in 11 years, almost 11 years. Why it happens in 11 years, we do not know. So I should tell you that there are a lot of things about sun which we do not know. For example, this is called solar cycle. And that solar cycle happens in 11 years. We do not know why does it happen. Solar flare, why solar flare is happening at a particular place, we do not know. What is solar flare, we do know, but why is it happening, we do not know. The goal of all solar missions is that let's try to find more about them. Let's collect more data, and let's try to find more about them, that can we predict that next solar flare, when is it going to happen and how does it happen, right? If we know how does it happen, then maybe we can also predict it, and accordingly we can perhaps invest into safeguarding us. There is another concept we should know, coronal hole. Coronal hole is certain places not in photosphere. Sunspots are found on photosphere. Coronal hole, as the name suggests, that is found in corona. There are certain places in corona where magnetic field is wide open. It is very weak. Magnetic field is very wide open. And when you see that with X-ray telescope, you have a telescope which is looking at things in X-ray, then you find this black hole-like structure, and hence the word coronal hole. And this coronal hole is directly related to the solar wind which I talked about. All the time charged particles coming out from sun, all of those charged particles come out of that coronal hole. So while coronal hole is associated with solar wind, which is an area of wide magnetic field found in corona, sunspot is on photosphere where temperature is very less, magnetic field is very high, and that is associated with solar flare and coronal mass ejection. So with all of that concept, now we can talk about that what Aditya mission is trying to figure out. Let me complete this. I will take all the questions. Let me complete this. Aditya mission is one of the most successful missions of ISRO. It does not get as much coverage as Chandrayaan 3, but the type of sophistication which was required to achieve this particular orbit, or where it is placed particularly, it's quite amazing. And just to give you a perspective, that it is almost 2.5 times farther than what Chandrayaan 3 reached. Chandrayaan 3 moon is about 380,000 kilometers, 3,80,000, and जो Aditya L1 mission है, that is at 1.5 million kilometers, which is 15 lakh kilometers. So more than 2.5 times farther away we sent Aditya mission. And to find that stable orbit at L2, L1 point, that in itself is quite difficult. Anyways, so Aditya mission, एक बार UPSC ने एस्ट्रोसैट मिशन पे क्वेश्चन पूछा था कि इसका मास क्या है, तो 1500 kg का आदित्य मिशन. I don't think they will repeat this question, but just to tell you a random information here, that this 1500 kg of payload, 1500 kg of instrument had 7 scientific payloads, and those 7 scientific payloads have their own specific objectives, जो आपके material में दे रखा है, but fundamentally they are going to monitor the data from chromosphere, from photosphere, and from corona. They will try to figure out the mechanism of coronal heating. They will try to know about flares, that X-ray flares which are there. They will try to know about solar wind as they travel through the interplanetary medium, the intensity. So Aditya mission is going to look into all of those things, all of those phenomena which I talked earlier. And so goal here is that we get to collect more data about sun, and accordingly we know more about sun and all of those solar phenomena here. And the last thing here, which I want to talk about, is that where Aditya mission is placed. So sun and earth ka jo average distance hai, that is about 150 million kilometer. Aditya mission is 1.5 million kilometer away from earth, so about 1% of distance of that 150 million kilometer. And Aditya mission is placed at a particular point which is called Lagrange point. It is named after the scientist who first theoretically predicted about Lagrange point. There was a scientist who lived about 100 years after Newton, that Newton had figured out why planets and stars are moving. He had figured about gravity, he had developed calculus, he had written the differential equations governing the motion of planets and stars, and he had solved those differential equations. Lagrange wanted to do something else. Lagrange wanted to do a thought problem. He did not even know that something like this is happening in the universe. He just wanted to figure out that what if there are 3 objects nearby. So if 2 objects are nearby, and if only 2 objects are exerting gravitational force upon each other, then we can figure out that what orbit they are going to execute. Jaise, there is sun, there is earth. And when I'm talking about earth's orbit around sun, then I'm not bothered about Mercury or Venus or Jupiter or Saturn, simply because compared to sun, these are very small objects. And compared to sun, unka jo impact hoga, wo itna kam hoga, that we can easily neglect that impact. Jaise, technically Jupiter has an impact on Earth's orbit. That impact is so less that we can easily neglect it. So when I'm describing Earth's orbit around sun, then I'm only bothered about sun and earth. I'm not bothered about any other object in the sky. We call such problem as two-body problem, and Newton figured that problem. Newton found answer to this 2 problem. Lagrange wanted to know that what if there are 3 objects, and I cannot neglect the gravitational effect of those 3. There are 3 objects in the sky, and all 3 of them have gravitational force exerted upon each other, then how they are going to move? Lagrange very soon realized that this problem is a very, very complex problem. It cannot be answered. It requires to solve really complex mathematics, which Lagrange did not know how to do that. Even today we do not know how to do that. We use computers for that. Wherever we are solving 3-body problem, we solve computers, we use computers for it. But Lagrange found a special case, and that special case was that what if the 2 objects are very heavy, but the 3rd object is very small. The 3rd object is so small that I can neglect the 3rd's mass compared to the other 2 objects. Then can I find solution? And to his surprise, when he solved his mathematics, he found that yes, there are solutions, there are stable solutions. And he found out that because of the 2 large objects, for example, let's say one large object as sun, let's take another large object as earth. Now, compared to sun and earth, Aditya mission ka mass jo hai 1500 kg hai. Now, compared to billion and trillion of kg, 1500 kg is negligible. So jo Lagrange ka jo assumption hai, wo bilkul fit baithta hai. Ki whatever Lagrange thought, that assumption fits here. So Lagrange assumed that let's do this calculation for this special scenario, and then to his surprise he found that there are 5 solutions, not 1, but there are 5 possible solutions for this 3rd smaller object. That if I keep this 3rd smaller object at either of these 5 points, then it gets to find a stable orbit, and that stability is not because of one of the object or another of the object, it is the combined effect of both of them. So I have object 1, I have object 2, and this is my object 3. And what Lagrange is telling us that this object 3 is going to find a stable orbit, and that stability is because of the combined effect of object 1 and object 2. But that is only and only going to happen if object 3 is negligible in mass compared to object 1 and 2, and for anything which we launch from Earth, that assumption will be true. So Lagrange did this a general calculation, that take any two large objects in the sky and try to solve this, and he found that this is true for any general two bodies, and we do see this. We do find it that for any two large object, we can find these 5 special points where the third object can find stability. And because in astronomy we are very much interested in collecting data from any scientific instrument, so the Sun-Earth system becomes very useful for us. So जो Lagrange का जो पूरा mathematical calculation, and by the way he had no idea that इसका कोई application होगा future में, but now we are actually using his calculation. So Aditya L1 mission has been launched at L1, that is one of the Lagrange point, but turns out there are 4 more. So for example, if I take Sun and Earth, my first object and second object, then there is a point between them, there is a point behind Earth, there is a point behind Sun, and there is a point perpendicular to this particular straight line. And what Lagrange mathematically showed, that at these 5 points, the third object is going to find a stable orbit. People have confirmed it now, and now many missions have been launched around L1 and L2 particularly. These two are very useful point, because think of L1 point, that L1 point, if I keep something here, as Earth revolves around Sun, L1 point also revolves around Sun, right? So if I keep something here, that object is going to revolve around Sun. So it is going to monitor Sun all the time. Why not to launch in a low Earth orbit? Why not to launch that in a low Earth orbit? And उसका आंसर बहुत सिंपल है, that if I keep something around Earth, which is bound only to Earth, let's say हमने 500 किलोमीटर पे किसी probe को launch किया, then half of the time it is going to come behind Earth. So it has to collect data from Sun, but Earth is going to create an eclipse half of the time. That, for example, I'm assuming that in this part of the sky Sun is, and as this orbit, as this spacecraft revolves around Earth, it is going to, Earth is going to come between this spacecraft and Sun. So Earth is creating an eclipse. Think about it. So whenever Earth is between this, it is not going to collect data about Sun. And that is going to happen half of the time. That half of the time it is not going to collect data about Sun. That is not good. And that is why जो L1 point है, that is very useful. That it can collect data about Sun all the time, and without any type of eclipse, without any type of impact. And the best part is that even though it is revolving around Sun closer to Earth, and as per gravity it should revolve much faster. So if Earth reaches here, something closer to Sun is going to reach here. Right? ये तो बहुत simple है ना, जैसे जो Mercury है, that completes its revolution in about 90 days. Venus completes its revolution in about 200, I don't know, 250 days, let's assume. And Earth completes its revolution in 365 days. So something which is closer to Sun compared to Earth should complete its revolution in less than 365 days. What it means is that as Earth revolves, this object is going to go much farther away from Earth. How will we collect data? हमारा पूरा purpose क्या है? That as we send this object, we want to collect data from it. We want to know more about Sun. If we cannot do that, then this mission is not going to be very helpful. And that is where L1 comes to rescue. That even though it is revolving around Sun, Earth का जो gravitational pull है, it is balancing it a little bit. And because of that, it is going to orbit around Sun exactly in 365 days. So if I keep a probe here, then that probe gets to maintain a contact with Earth all the time. And at the same time, it also gets to collect data about Sun all the time. You have best of both the worlds. So that is why L1 point is generally chosen for solar observation. And Aditya is not the first mission here around L1 point. You have a very famous mission of NASA called SOHO mission. I do think we should know about it. Solar and Heliospheric Observatory. That is the full form of this mission. Heliospheric Observatory का मतलब होता है something which is around Sun. Heliospheric orbit का मतलब होता है something which is orbiting around Sun. So SOHO mission is quite an old and a very famous mission which already is around L1 point. But in any case, the number of missions around L1 point, we can literally count that on finger. Hardly 4 or 5 missions are there around L1 point. And that is what makes this particular achievement quite tremendous. It took 4 months to reach there, right? It took 4 months for this Aditya L1 mission to reach to its desirable point, and finally we have been able to successfully achieve this orbit, and it already has started collecting data and it is sending that data back to ground station. L2 point is very useful for astronomical observation. I can send a telescope there, and that telescope can look at the night sky, at the deep space. It can collect light from the deep space without coming in shadow of moon or earth, and it can also send that data back to earth all the time. That is where James Webb Space Telescope are, and that is where recently Euclid mission of European Space Agency was launched. I'm going to talk about both of them briefly in subsequent topic. So that's it. I do think I will repeat everything which I have said, and I do think that this should be more than enough, particularly for prelims examination. The first thing which I told you, that Earth has various layers. Aditya L1 mission is going to monitor or collect data about the outermost 3 layers, which is photosphere, chromosphere, and corona. And one thing which I missed here, that it is not going to collect data just in visible light. जो instruments of Aditya mission hai, some of the instruments they can collect X-ray also, some of the instruments can collect UV also, and some can also collect infrared along with visible light. So Aditya L1 mission is going to collect data in 4 frequency band, in X-ray, in UV, in visible, and in infrared light. And the goal here is to know more about the outermost layer, photosphere, chromosphere, and corona. And the reason we want to know about this 3 outermost layer is all of those events which we talked about, be it solar wind, be it solar flare, or be it coronal mass ejection. And then last but not the least, I also told you that Aditya had 7 payloads. Those 7 payloads are going to collect data about everything which we talked about. But Aditya is placed at L1 point, which is 1.5 million kilometers away from Earth towards Sun. And at that point, the gravitational effect of Sun and Earth together provides the necessary centripetal force for Aditya mission to find a stable orbit. And this is not the only mission which is at L1. You have in past SOHO mission of NASA. And L2 point jo hai, that is quite useful for astronomical observation, where Webb telescope or Euclid mission of European Space Agency, they have been launched here. If you have any question now, you can ask questions. And I will repeat that this is one of the most important topics which for prelims examination. Yes, go ahead.
सर L3 पॉइंट जो है काफ़ी दूर है अर्थ से और सन से भी, तो सर वहाँ नेग्लिजिबल नहीं हो जाना चाहिए?
देखो 2 चीज़ें हैं. क्वेश्चन है कि L3 पॉइंट, सबसे पहले तो L3 ऐसे भी हमारे लिए यूजफुल नहीं है. अगर हम मान लें कि यहाँ पे अगर हम कुछ लॉन्च कर भी देते हैं एट L3 पॉइंट, तब भी हमारे काम का नहीं है, बिकॉज इट इज़ गोइंग टू बी बिहाइंड सन ऑल द टाइम. दैट इज़ द फर्स्ट थिंग. Second thing, this entire calculation for Sun and Earth is also based on this assumption that Sun, Earth and third object जो है उसके अलावा कुछ भी नहीं है. But ये assumption गलत है. हमको पता है कि Mercury है, Venus है, Jupiter है. So you are absolutely right. ये जो mathematical calculation which is showing us the distance of L3, it is a mathematical calculation based on an assumption that there is Sun, Earth and there is the third object, nothing else. It does not assume anything else. And in that assumption, if you calculate L3, it is going to be this far away. And no, you will find a stable orbit because of both Sun and Earth, right? But even if there was nothing else, even then this point is not useful, because यहाँ पे जो भी probe होगा वो हमेशा Sun के पीछे होगा. तो हम इसे connect कैसे करेंगे? How are we going to collect data from here? So it's not going to be very useful, right?
तो सर यहाँ पे ग्रेविटेशनल फोर्स दोनों की ऐड हो जाएगी?
हाँ बिल्कुल ऐड होगी. वो तो L2 पे भी ऐड होगी, L3 पे भी ऐड होगी और L2 पे भी ऐड होगी.
L2 और L3 पर
बिल्कुल.
और L1, L4 और L5 पर दोनों बैलेंस करेंगी 3.
देखो यहाँ पे अब L4 पे देखो क्या है कि there is a attraction and there is attraction. इसका जो net effect होगा that will be towards sun only, right? And that net effect will be very much towards the center of the sun. and that is how it is going to find a stable orbit. तो पांचों पॉइंट पे अर्थ और सन का कॉम्बाइंड इफेक्ट होगा, ऐसा कोई भी नहीं कि खाली एक पॉइंट पे है. इन पांचों पॉइंट पे जब हम बात करेंगे it will be combined effect of both sun and earth. ठीक है, so it's not just for L4 and L5, also for L1, L2 and L3. Any other question?
Sir,
Just a second. हाँ जी.
Sir, since Lagrange point, at Lagrange point, both the gravitational force of Earth and Sun seems to be cancel one another.
Why would I say that? I never said that. So I never said that they're going to cancel one another. That will be a wrong statement. What correct statement will be that the Sun's gravitational pull will be counterbalanced a little bit by Earth, so that an object around L1 point keeps orbiting around Sun exactly in 365 days. So the correct statement here will be that at L1 or at L2 or L3 or at L4 or at L5, the combined effect of Sun and Earth is enough to provide the necessary centripetal force for the third smaller object to find a stable orbit. That will be a correct statement.
Okay, sir, since it would be a stable orbit, so can this point be also used for future missions as a launching stations?
Okay, now that's a very interesting question. So first, they are not very stable point. So L1, L2 and L3 point hai, they are not stable. L4 and L5 are stable point. I don't think we have to go into this technicality, but since you have asked this question, let me answer this. ये जो दो point है, these are stable points. Physics में stable point का एक बहुत specific meaning होता है. Whenever we are using the word stable point, it has a very specific meaning. And I can show that with the example of that. Imagine a pot here, a hemispherical pot, and imagine that I keep something at the bottom of the pot. If I replace this in any direction, and imagine all direction in 3D, I can move that in any all the direction, possible direction. This object is going to come back to its equilibrium position. L4 and L5 are like that. Okay. There is also a point when I put this top at the box, I keep something here. At one point it will remain stable, but if I replace it a little bit, it is going to fall down in any direction. In any direction I replace, little bit displace, it is going to fall down. So L1, L2 and L3 they are what we call semi-stable point. So they are not completely unstable, but they are also not completely stable. If you have ever seen a horse saddle, horse का saddle, horse पे बैठने से पहले आपने एक saddle देखा है? So if you can imagine that saddle shape, that saddle looks elevated from both sides, but it is declined from the side where you keep your legs. That is very important to have stability. Horse अचानक से रुक जाए, आप आगे नहीं जाओगे, right? But at the same time पैरों को जगह चाहिए. So आप imagine करो a horse saddle that in two direction if I replace things, it is going to come back, but in other two direction it is going to fall down. L1, L2, L3 are like that. So L1, L2, L3 they are not stable, they are what we call semi-stable point. And because of that semi-stability, whatever we have to launch, we need to actually keep lot of fuel there. That all the time we have to generate little bit of thrust so that they get to maintain their stable orbit. Even if their orbit changes, even if let's say for example, because of any factor, their position gets changed a lot, and they let's say they start making a motion towards sun, it will be very difficult to reverse that motion. So L1, L2, L3, these are not stable point. These are what we call semi-stable point. L4 and L5 are stable point. And if I keep something at L4 and L5, then yes, we can have a very large station at L4 and L5. It's very popular in science fiction already. It's not at all closer to reality. There is no plan of any space agency to make a space station at L4 and L5. Maybe in future we will. But L1, L2 and L3, they are not stable. They are what we call semi-stable point. In nature it functions, by the way. जो L4 and L5 का जो stability है, in nature we can witness that. There is a topic which I am going to discuss later. अभी discuss कर लेते हैं जल्दी से. NASA का एक mission है, Lucy mission, that is going to study Trojan asteroids. आपके material में दे रखा है ये. Just let me complete this, then I will take your question. तो इसमें बस एक लाइन में आपको पहले ये भी पता होना चाहिए that NASA has a mission called Lucy mission, which aims to study Trojan asteroids. You look at solar system, you find that between Mars and Jupiter there are millions of these small asteroids. But apart from this one group of asteroid, we also find that you have asteroids here and you have asteroids here. Apart from the white one which you see, you find these two group of asteroids, one group which is preceding Jupiter, another which is preceding Jupiter. And these two group of asteroids, they are called Trojan because they were roaming around here and there, but they were captured by Jupiter's gravity. But this orbit around Sun which they have is not only because of Sun, but also because of Jupiter. And they are at L4 and L5 point of Sun-Jupiter Lagrange point. I told you that any two objects can have two set of Lagrange point. So the Sun-Jupiter का Lagrange point है, particularly the L4 and L5 point. Many of the asteroids roaming around here and there, they get captured around this particular point and then they stay there. So this orbit around Sun is not only because of Sun's gravity, it is also because of Jupiter's gravity. So in nature we already find this stable point of L4 and L5 point. In nature we already get to see that. Lagrange did not know it, but now we know it. That in nature जो है L4, L5 point, उसका जो impact है, we can actually witness it. You had a question, इनको जरा mic दीजिएगा.
Sir, if solar storm or coronal mass ejection enters the Earth atmosphere, then it will disrupt the Earth weather system?
It can disrupt the space weather, right? Because Earth का जो weather system है, the question is, everybody heard the question. जो Earth का weather system है, that depends upon the type of sunlight on an average we receive, that depends upon temperature, pressure, wind velocity, moisture content, all of those things affect it. We use a concept called space weather. Space weather is what is happening in the outer atmosphere and up to thermosphere or जो पूरा exosphere है, what is happening there. And space weather gets affected by solar particles, right? So saying that it is going to, let's say for example, impact planetary wind system, or it is going to impact some pressure variation on Earth, that will not be correct. But does it affect space weather? Does it affect the concentration, energy, density of charged particles in the outer space? The answer is yes, it does. So not the weather pattern, planetary wind system or pressure belts which we have, it is not going to impact that, but it is going to impact the space weather. हाँ जी.
Sir, in case अगर वो अर्थ के एटमॉस्फेयर में एंटर जाएगा तब भी कोई डिस्टर्ब नहीं होगा वेदर्स में?
बहुत ही, अगर ऐसा क्यों होगा? ऐसे क्यों होगा कि जैसे फॉर एग्जांपल अगर ये है भी तो ये बहुत ही ऐसे समझ लो कि स्पॉन्टेनियस तात्क्षणिक फिनोमेना है. इट इज गोइंग टू वट एवर चेंज इट इज गोइंग टू कॉज इंस्टेंटेनियसली एंड इट इज नॉट गोइंग टू कॉज एनी चेंज आफ्टर दैट. जो वेदर की भी हम बात करते हैं, भले चलो वेदर हम दिल्ली की भी बात करते हैं, तब भी दिल्ली में भी हम पूरे एक दिन की बात करते हैं, और क्लाइमेट तो हम एक पूरा एवरेज की बात करते हैं, तो उसमें ऐसे कुछ मेजर चेंज नहीं होना है ऑन अर्थ्स क्लाइमेट सिस्टम पर्टिकुलरली. ठीक है.
एंड व्हाट इज अ सन हेलोज एंड मून हेलोज करके होता है, जो एक रिंग स्ट्रक्चर फॉर्म होता है सर सन एंड मून के अराउंड, सर उसका क्या रीज़न है और वो क्यों होता है सर?
सोलर हैलो एंड
मून हेलो, मतलब सन हेलो एंड मून हेलोज.
हैलो जो हमको सन के अराउंड कभी कभी दिखता है, वो तो एटमॉस्फेरिक फिनोमेना है, जो एटमॉस्फेरिक पार्टिकल्स हैं, इसी तरीके से वो रेनबो दिखता है, तो रेनबो हमको दिखता है बहुत सारी चीज़ों का डिस्पर्शन के कारण, तो वो एटमॉस्फेरिक फिनोमेना है, दैट लाइट गेट्स filtered in a way that you find a halo around sun. That's atmospheric. It has nothing to do with whatever we have discussed here. That is something to do with how our eyes are collecting light because of atmospheric particles. Any other question?
Sir, जो coronal mass ejection है सर, वो thunderstorms वगैरह बढ़ा सकता है? क्योंकि सर, लेकिन सर thunderstorms भी तो charged particles से lightning होती है जैसे.
Okay, हाँ ठीक है, इस सेंस में.
Yes sir.
देखो एटमॉस्फेयर में ऑलरेडी जो अर्थ पे और एटमॉस्फेरिक आउटर एटमॉस्फेयर में चार्ज पार्टिकल कॉन्सेंट्रेशन है, एंड यस इफ आई थिंक दैट इन दैट वे देन यस मे बी द आंसर इज यस, बट वी विल हैव टू फाइंड द एग्जैक्ट मैकेनिज्म हाउ इट इज गोइंग टू हैपन. सो द शॉर्ट आंसर इज दैट यस इट कैन हैपन, बिकॉज जो थंडर स्टॉर्म है इसेंशियली इट इज दैट पोटेंशियल डिफरेंस बिटवीन अर्थ सर्फेस एंड एटमॉस्फेयर, एंड दैट पोटेंशियल डिफरेंस कॉजेज अ वेरी पावरफुल थंडर स्टॉर्म, एंड यस दिस पोटेंशियल डिफरेंस कैन बी अफेक्टेड बाय outer space weather. So the answer is yes, it can happen.
Sir, how these coronal mass ejections are related to geomagnetic storms?
Geomagnetic storm is a common word which we are using for multiple things.
Okay.
Geomagnetic storm simply means that as particles, charged particles, interact with Earth's magnetic field, what is going to happen? And all of that which is going to happen collectively together, we are calling it geomagnetic storm. So whenever charged particles are interacting with Earth's magnetic field, we call this geomagnetic storm. In fact, naam se bhi clear hona chahiye. Geo means Earth, magnetic, we are talking about Earth's magnetic field. So how they are connected to geomagnetic storm? Because coronal mass ejection is essentially charged particle. It is essentially plasma. And that plasma interacts with Earth's magnetic field. And yes, this impact can be, as I said, it can be aurora also, but it can also be power blackouts. So that is how they are connected. Okay.
This Aditya L1 mission और चंद्रयान 3 ये वो मतलब लोअर अर्थ ऑर्बिट और मीडियम अर्थ ऑर्बिट कहाँ पे वो प्लेस होता है?
बिल्कुल भी नहीं है, दोनों ही लो अर्थ ऑर्बिट से कोई रिलेशन ही नहीं है. जब हम लो अर्थ ऑर्बिट की बात करते हैं देन वी आर इसेंशियली टॉकिंग अबाउट एन अर्थ बाउंड स्पेसक्राफ्ट जो कि 200 से 2000 किलोमीटर तक है. जो आदित्य मिशन है वो अर्थ बाउंड भी नहीं है. आदित्य मिशन का जो ऑर्बिट है इट इज स्टेबल बिकॉज ऑफ अर्थ बट इट इज इसेंशियली अ सोलर ऑर्बिट.
वो जियो स्टेशनरी ऑर्बिट
नहीं है, जियो स्टेशनरी भी नहीं है. अगेन व्हेन आई एम यूजिंग द वर्ड जियो स्टेशनरी then I'm talking about something which is at 36,000 kilometer around Earth. It is not around Earth, it is around Sun. So the term low Earth orbit or medium Earth orbit or high Earth orbit will not fit here. जो हमारा definition है, the definition we cannot use it here. And same is also true in case of Chandrayaan 3. Chandrayaan 3 finally found a lunar orbit. So if something is lunar orbit or solar orbit, then why would I use the definition of earthbound orbit? Yes.
सर ये आपने बताया है सोलर विंड का stream of charged particle that come all the time है ना?
सोलर more recurrent phenomena.
Okay सर, सोलर फ्लेयर है जो very bright light है सर, वो कब होता है?
देखो सोलर फ्लेयर तब होगा जब सन स्पॉट एक्टिविटी बहुत ज़्यादा हो एंड पर्टिकुलरली जो मैग्नेटिक फील्ड हो बहुत स्क्वीज्ड हो एंड व्हेनेवर दे रीअलाइन देन इट कैन रिलीज दैट ब्राइट लाइट एज वेल एज दैट प्लाज्मा. So that has to do with solar sunspot activity, while solar wind जो है that has to do with the coronal hole which I talked about. Yes, go ahead.
Sir, with respect to UV rays type C, does the Earth completely blocks it or some part of it reaches Earth?
Okay, that is an entirely separate question. I will divide that in two parts. The first what you asked is that UVC most of the ozone layer filters out most of the UVC. But I will relate that to the topic I am discussing. That can solar particles affect ozone layer? The answer is yes, it can. Ozone layer can get depleted because of solar particles. So if that is your question, the answer is yes. Solar flares or coronal mass ejection, they can have negative impact on ozone layer. Right? And if that happens, then ozone layer का जो ultraviolet light filter करने का जो capacity है, that capacity gets adversely affected.
So if it affects this ozone layer, so it can reach Earth and like can affect the human skin?
Yes, temporary it can. Any other question from this topic? We have many more topics, so be very careful in questions you are asking. Yes, go ahead.
Sir, in terms of L3 and L4, the
combined... Or L4 or L5?
L4 and L5. So the combined effect of Earth and Sun makes the L4 point or whatever is placed in L4 and L5, the combined effect makes it revolve around the sun in a particular orbit due to the combined effect. Is it so?
Yeah, it is. Yeah.
That's it.
Okay. Any other question? Let's take a small break here. After that, we will resume the class. But I took so much of time in this topic because I also think that this is one of the most important topic from space technology. I expect various types. We can have various types of questions. There can be some conceptual questions like meaning of Lagrangian point, or about sun layers, or about coronal mass ejection or solar flares, things like that. But there can also be factual questions, such as the fact that Aditya L1 mission was launched by PSLV, things like that. So I expect many types of questions can be made. So I do expect at least one question inspired from theme or directly from this theme to be asked by UPSC. I can also expect a question like that there have been given 2-3 names of these payloads and you are supposed to know that they are payloads of Aditya L1. So यहाँ पे ज़्यादा मुश्किल नहीं, एक factual question जहाँ पे 2-3 payload का एक साथ नाम दे रखा है, and you are supposed to know that these are payloads of Aditya L1. I consider Gaganyaan mission to be much more important for mains examination, but few factual things about Gaganyaan mission should be clear. That if India becomes successful, we will be the 4th country to do that after Russia, US and China. I briefly wanted to tell you about Van Allen radiation belt also. Although not covered in your material, but since we are talking about solar particles so much, we should know about Van Allen radiation belt. That when we monitor Earth, we find that around Earth, there are 2 zones, looks like this, where the concentration of charged particles is very high. And these charged particles essentially are solar particles which are trapped by Earth's magnetic field. So these 2 zones, we call them Van Allen radiation belt, named after the scientist who first discovered it. The understanding of Van Allen radiation belt will help us in understanding about space weather, as well as that zone it needs to be avoided for satellite launches, or the errors it can cause for GPS satellites, things like that. So, but nonetheless, we should know that Van Allen radiation belt is nothing but a zone within Earth's magnetosphere where the concentration of charged particles is high, and essentially those charged particles, most of them are solar particles. They have come from solar wind or coronal mass ejection. Gaganyaan mission is planned in 3 phases. First, there will be unmanned mission, which is going to mimic Gaganyaan mission. Second, an unmanned mission with Vyomitra as the astronaut, as an AI robot. And then, of course, we have now the 4 crew member. I think either 2 or 3 of them will be part of Gaganyaan member crew. And we are going to use LVM-3, which I talked about earlier, which is our most powerful rocket. 3 stages. There are 2 solid boosters. Second is this liquid stage, and third is this cryogenic stage. We call this cryogenic stage as C25 engine. I do think that we should know about it. We call that liquid engine as Vikas engine. So the liquid engine है ISRO का, that engine is called Vikas engine, और जो cryogenic engine है, that is called C25 engine. Cryogenic simply means that the fuel and oxidizer, they are stored at very low temperature, less than minus 150 degrees Celsius. And it can provide, despite having less amount of fuel, it can provide lot of boost. And there are many planned things. ISRO has all of these things planned. Many of those things already have occurred. The goal here is that we want to ensure that each and every part of any type of failure should not happen in Gaganyaan mission. So ISRO has done many testing, high altitude scape or propulsion characteristic test or integrated parachute airdrop test. So many of this testing already has occurred successfully. Pad abort test, that if there is failure in launching any type of time, we want to abort the mission. Or even we are going to have this unmanned flight, and finally we will have this manned flight. So even before Gaganyaan mission, there are multiple other missions. Some of them already have been successfully done by ISRO, and some more will be done in coming months, which will be in newspapers. And finally Gaganyaan mission will be launched perhaps next year, or next year ही plan है, 2025 का plan है अभी, but exact अभी क्या date होगा ये अभी clear नहीं है. The earlier plan was for about 6-7 days, but now we have reduced that to 3 days. That 3-day mission into low Earth orbit of about 400 to 500 kilometer, a crew of either 2 or 3 members who are going to spend the time around Earth and then they are going to come back. The challenges of Gaganyaan mission, all of those things, I think they are much more important for mains examination rather than prelims examination. But आप ऐसे सोच सकते हो that we have to make space habitable, which basically means that you learn to survive in this microgravity condition. You learn to survive, you need to carry all the essential things for life, for example, water or oxygen, because you do not have that. And you need to invest a lot into recycling system, waste management system in each and every part of it so that there is no infection per se. And then you also need great mental fortitude that you get to away from civilization even for few days. And in such tough, harsh condition, you get to survive there. So that also requires mental fortitude. So anyways, I do think that the challenges wala part hai, that is much more important for mains examination, or why we are doing something like that, why we are spending 10,000 crore rupees on Gaganyaan mission. Always there can be a question that why India is not spending that on poverty alleviation program. But such type of themes I expect in mains examination, not in prelims examination. If you have any question from this topic, you can ask. So technical kuch nahi hai. So there are certain factual details which you should know. 3 days low Earth orbit. Even before Gaganyaan, there are unmanned missions which are planned. Multiple things have been demonstrated by ISRO to ensure that each and every part of this mission goes on smoothly and successfully. So these are factual details which we should know, and perhaps 1 or 2 facts can be asked by UPSC, but इसमें कुछ technicality नहीं है. India will be the 4th country to have something like that. That is also important factual detail. Navigation with Indian constellation, NAVIC as we said, the regional navigational satellite system. Navigational satellites का purpose बहुत simple है. They tell you where you are on Earth, right? So they tell you your latitude, longitude as well as altitude. They also help us in timing. They tell us about accurate time as each and every second is passing. GPS clocks make a record of it. So not just position, but also for accurate timing, we use navigational satellite systems. We always need at least 4 satellites in the sky. And if I have any receiver here, for example, let's say this mobile phone has a receiver, electronic receiver, then it needs data from minimum 4 satellites to figure out where it is on planet Earth. It's very similar to triangulation, but the only thing is that 4 spheres are required. The GPS has a very precise clock. A GPS sends a data to electronic receiver somewhere on the ground. It takes some time, and based on that time, a GPS, one satellite knows how far that object is. But if it only knows how far that object is, then it can make a sphere, and it can tell you that anywhere you are on that spherical surface. So that is why we need data from second satellite, and we need data from third satellite, and we need data from 4 satellite, because if you go into solid geometry, you realize that 4 spheres connect at 1 point, 3 spheres connect at 2 points. So the final accuracy hai, that will come from 4th satellite. So we always need 4 satellites to know precise location. And that also tells you that why NAVIC is only a regional navigational satellite system, because NAVIC comprises of 7 satellites, 4 of them are in geosynchronous, 3 of them are in geostationary orbit. And since they are in geosynchronous and geostationary, as Earth rotates, the satellites are going to revolve around Indian subcontinent upar. So all the time, they will always be above Indian subcontinent region. So any place in India, and as per ISRO website, 1500 kilometer beyond India's border, if we want to know precise location, we can rely upon NAVIC. Compared to satellite systems like GPS, which are global in nature, just say in this animation, that red point on Earth, as Earth rotates and its satellites revolve, GPS satellites revolve, you get to see that this point always is in the line of presence of at least 5, 6 or even 7, 8 satellites. So that is why GPS is a global navigational satellite system, that anywhere you go on planet Earth, all the time at least there will be 4 satellites in the sky which can tell the precise location. While in case of Navik, you only have 7 satellites. To make it global, we need to launch more satellites. We need to have more and more number of satellites along different position. So US is not the only country to have this. Apart from US, you have Russia, which has GLONASS, or you have China, which has BEDOU, or you have Europe, of course, which has Galileo. And even Japan has a system. But Japan का भी again जो system है वो independent system नहीं है. That only is a correction mechanism in GPS satellite. What is Japan's system's name? QZSS, Quasi-Zenith Satellite System. So Japan का जो satellite system है, that is called QZSS, Quasi-Zenith Satellite System, but that is not independent. That makes correction to GPS satellite, and it can only make that correction in Asia Pacific region. In contrast, जो Navik है, that is an independent system. It is not reliant upon any BEDOU or Galileo or GPS for that matter. Navik खुद में एक independent navigational satellite system है. The only thing is that it is only going to provide this precise location just above Indian subcontinent region, not a global system. Right? These are some basic things. इन सब पे UPSC ने past में question पूछ रखा है, आगे भी पूछ सकती है. One of those satellites recently was replaced with a new generation of navigational satellite, which is called NVS-01, जिसके कारण ये topic आपका news में दे रखा है. Along with the fact that government of India is planning to make microchips which will be integrated with Navik. That will be quite useful for a type of services which we call restricted services. All navigational satellite provides 2 types of services. The first is called standard services, which is used for civilian uses such as we use it in our day-to-day life. But the second is called restricted services. That restricted services, as the name suggests, is restricted to military people, people of intelligence officials. And those restricted services are much more precise when they're determining location. So think of all of the weapons which are guided by GPS. They require much more precision. And in such cases, that restricted services can be quite useful. So, and why India needs to have a Navik? One of the most important objective here is to better equip ourselves in case of restricted services. We are blessed with good neighborhood, and we want to ensure that at least for restricted services we have capability in defense sector. But again, it can have applications for civilian uses also. And that is also a demand by Government of India. It is asking all mobile phone manufacturers that your phone should have a Navik receiver apart from GPS receiver. There is one more navigational system of ISRO which we should know about. अभी तक UPSC ने इसमें क्वेश्चन पूछा नहीं, although बहुत पुराना सिस्टम है. It predates Navik, but it is not as such an independent navigational satellite system. It is a system which includes a lot of things. It is a system which fundamentally is based on GPS only. But the GPS data is collected by various data centers at the ground. And that data is processed by some really powerful computers, that even if there is some error, those errors can be rectified. And that processed error-free data can be now transmitted to, let's say, airline sector. इसका जो सबसे important use है गगन का, as the name suggests, that is for civilian aircraft movement. That जो civilian airline movement है, we are using it, but we can use it for other areas also. Wherever we have to make navigational services, we can use Gagan infrastructure. So I will repeat Gagan per se. गगन जो है ये खुद का कोई इंडिपेंडेंट navigational satellite system नहीं है. Gagan relies upon the GPS satellites. So it relies upon GPS satellites. It collects data from GPS satellite. The data gets processed at many computing centers to take care of any type of error. And that error-free data now can be provided to airlines. And that is quite useful for overall civilian aircraft movement. So जो पूरा गगन system है, that is a collaboration between ISRO and Ministry of Civil Aviation. Ministry of Civil Aviation has a particular body called Airport Authority of India. and they both collaborated together and they invested into this system called Gagan. So I will repeat, Gagan predates Navik for that matter. And one thing which was in news, which we should know here, it's Sagar Sampark. That Ministry of Shipping now, they are also trying to do the same thing. That they want to provide precise information to the ships and boats which are used for trading or even for fishing. And this entire setup which ministry is investing into, that entire setup is called Sagar Sampark. So ये बस एक लाइन में हम याद रखेंगे, दो चीज़ें याद रखेंगे, that सागर संपर्क का ऑब्जेक्टिव क्या है और कौन से मिनिस्ट्री का है, that's it. इससे ज़्यादा I do not expect any other type of question in prelims examination. Just two things here, that what it does and which ministry has launched this particular initiative called Sagar Sampark. Any question here? The next topic, explaining and appreciating the concept of gravitational wave in a limited time frame is not an easy thing to do. So I will start with that limitation first, that there are limitations. I will promise you one thing, that whatever I am going to discuss or whatever points I am going to mention, if you can recollect those points, then I don't think there will be more. If this topic is asked, there will be a question beyond that. I will try to explain it, but it's not a very easy concept to grasp too. The first thing, because it fundamentally challenges how we perceive world around us. So पूरा concept of gravitational wave है, it comes from Einstein's general theory of relativity. There is a reason why Einstein is considered as the greatest scientist who has ever lived, because of two theories he gave. The first theory is called special theory of relativity, and second is called general theory of relativity. So I'm going to explain each and every part of this news. I frankly do not think that UPSC will ask if this theme is, by the way, this theme has been picked by UPSC at least twice or thrice in previous years, but all the time questions have been very simple and very straightforward. You're just supposed to know about objective of a particular observatory, and the answer was gravitational wave, or you are supposed to know two things about gravitational waves, things like that. Why I made a statement that it is difficult to comprehend? Because Einstein challenges our conception of the universe. Before Einstein, everybody assumed in absolute time. Before Einstein, people thought of relative velocity, relative distances, but nobody questioned the time itself. That everybody accepted that time remains absolute. Time is not at all dependent upon the observer. Einstein challenged that. Einstein made a statement in special theory of relativity. In fact, special theory of relativity का consequence ये है that space and time are not two different things. Space and time are part of one continuum. We collectively call it space-time continuum. So what does it mean is, I will make a very simple statement. I will not go into more than that. That if I drop this pen, and let's say this event happened in 1 second, then before Einstein, each and every scientist will say, and each and every philosopher will say, that no matter who observes this, कोई भी ऑब्जर्व करे उसके लिए ये जो पूरा इवेंट है, ये जो ड्रॉपिंग ऑफ पेन है, दैट हैज हैपेंड इन जस्ट 1 सेकेंड. और वन मोर थिंग, दैट इफ आई टेक two objects, 2 points in space, and I say that they are separated by 1 meter, the distance between 2 points, then before Einstein, each and every scientist and every philosopher will say that no matter who measures this is going to find that to be 1 meter. Einstein says that that's not the case. Einstein says that space and time जो है, that in itself is relative, and that depends upon how fast you are traveling. And all of that comes from a very basic consequence of Einstein's theory, special theory of relativity, that speed of light is constant no matter in which frame of reference you are. What does that mean? Imagine an object A here, and imagine an object B there, traveling in 2 different directions with speed V and V, and imagine both of them are traveling in the same direction with V, exactly in the straight line. In the first scenario, if A measures speed of B, then जो हमारा traditional logic और जो भी हमने physics अभी तक पढ़ रखा है, उसके हिसाब से A is going to measure that B is traveling with velocity 2v. That makes sense, right? A is traveling in opposite direction, B का distance twice per unit time बढ़ते चले जा रहे हैं. So A is going to measure that B का जो velocity होगा वो 2 times v होगा, and B is also going to measure the same for velocity of A. But in the second case, both of them are going to measure that we are rest with respect to each other, right? We are not changing our distance, so we are at rest with respect to each other. Einstein says that in very low velocity ranges, ये हमारा formula ठीक है. But जैसे जैसे velocity बढ़ते चले जाएगा, पहले तो ये formula गलत होगा. And दूसरी चीज, that if this velocity exactly becomes c here means speed of light, which is 3 lakh kilometer per second. And then Einstein says that if something is traveling with speed of light, then if A measures speed of B, then A is going to find that B is traveling with speed of light only, c only. And B measures speed of A is going to measure again c only, not 2c, not 2 times c. And similarly, in the second case also, both A and B are going to measure each other's speed at c only, not 0, unlike in the first case. And that has to do with how we perceive space and how we perceive time. And that has to do with the fact that space and time are not different from each other. We actually live in a 4-dimensional world. The 3 dimensions are spatial dimension, but the 4th dimension is time dimension. The only difference between spatial dimension and time dimension is that in spatial dimension we seem to be, it is possible to go anywhere, up and down, right and left, sideways. But in time dimension we only go in forward. That is an entirely different reason. But apart from that, spatial dimension and time dimension, they are not independent of each other. They are very much dependent upon each other. This theory is called spatial theory of relativity. And spatial theory of relativity has certain consequences. I'm going to mention at least few of them. And if you can remember that also, that is more than enough. The first is that nothing can travel with more than speed of light. There is a barrier there. You cannot cross that barrier. And to travel with speed of light, you need to be massless. That आपका rest mass अगर 0 है, only then you travel with speed of light. जैसे photons are massless, and that is why they travel with speed of light. Gluons are massless, they travel with speed of light. But anything which has mass, it cannot travel with speed of light. It can come very close to it, but can never travel with speed of light. That is the first consequence. The second consequence, that the entire notion of distance, length and time is not absolute. Length can contract, time can dilate depending upon how fast you are moving. If you are moving very fast, you are going to see length contraction, time dilation. If you are moving very fast, length will be shortened, time will be extended for you. How time passes for you if you are moving very fast versus somebody who is moving very slow, how time passes for that person will not be the same. In your frame of reference, जो आपका time है वो अभी भी same रहेगा, but the other person is going to age faster compared to you. For you, the time will be slowed down. So this does not make, that is why I said that it is difficult to explain, because prima facie does not make sense. Believe me, it does make sense once you go into some deeper concepts such as causality. So, but nonetheless, prima facie does not make sense that there is nothing called absolute time. All of us assume that time is absolute. Einstein questions that time is not absolute. But things become much more weirder when Einstein gave his general theory of relativity. In general theory of relativity, he now makes a statement that forget about space-time, which by the way are same, but the entire space-time curvature in itself is affected by gravity. So Einstein says that you can imagine that space-time as one fabric, and imagine a very massive object, that this massive object is distorting this fabric. Imagine literally a fabric, आप एक कपड़ा imagine करो and imagine that something has been kept here. It is going to distort the overall जो fabric का पहले configuration है. And now imagine that if you put something there, then it is going to move around it. So what you experience as a attractive gravitational force is actually not an attractive force. It is a consequence of that fabric of space-time which has now become curved because of heavy objects. So the heavier the object, the more impact it will have on the fabric of space-time. People often use this picture where we imagine fabric, a two-dimensional fabric, and we keep something heavy and we imagine that this fabric has become curved and the other object is now moving around it. So sun के कारण जो curvature है, in that curvature earth is moving, and earth के कारण जो curvature है, moon is moving. The reality will be, of course, that space is three-dimensional. So reality will be something like this, that as objects move, the space contracts around them as they move because they are quite heavy. So in Einstein's general theory of relativity, gravity is not a force. Gravity is a consequence of space-time curvature. So now he is saying that space-time to same hai hi hai. Space-time curvature is affected by gravity, and the more powerful or the more heavy an object is, the more distortion it is going to cause into space-time. What it means is that if you are near a heavier object now, the time gets to slow down for you compared to, again, you are not going to witness that, but compared to near a very heavy object, time for some other observer near a lighter object will be different. For example, somehow if you get to survive on sun, on the surface of sun, let's say you get to live for 80 years, that is average human life right now. And if you return back on earth, then you find that more than 80 years have passed on earth. Maybe it is 80 years plus one day. But if remove that sun with black hole or a neutron star, then every day can become a year also. You spend a day around black hole and some few years have passed around a planet. So the heavier object you are around with, the time slows down. Again, in your frame of reference, the time is exactly as what it is. But for an object, for a person, for a frame of reference, which is at around lighter object, that time gets to, in that observer, the time for the observer around heavier object gets to slow down. So, but nonetheless, without going into complication, only one line, just let me complete this, only one line, that I don't ask question in this topic. Whatever I'm discussing, whatever I'm talking about, just note it down. Doesn't make sense. It doesn't make sense. I'm only covering the part which UPSC can ask question from, and we should be prepared for it. That's it. So, heavier object, they will cause more distortion in space-time, and that is going to cause lighter object move around it. So, gravity affects space-time, and yes, gravity can also lead to time dilation. That how time passes for a heavier object, for a lighter object, that will not be same. When Einstein gave this theory, very few people understood it, and even lesser people accepted this. But Einstein was proven right again and again, and many of those predictions he made in 1920s, many of those predictions are coming today, even today they are coming out to be true. So many of those predictions, for example, one of the prediction his theory made that universe is expanding, and Einstein did not believe that to be true. Einstein thought that this is a wrong prediction, and he felt that his theory is wrong. But turns out he was wrong and his theory was right. And universe expansion, that was actually proven to be right, that universe actually is expanding. His theory also, general theory of relativity also theorized or also predicted that black holes are a reality. Not done by Einstein himself, that was done by a great physicist who is even today alive, now in his 90s, Roger Penrose, one of the smartest people alive right now. So Roger Penrose predicted in 1950s that if Einstein theory is correct, then there is no doubt that black hole can exist by mathematics. He mathematically proved that black hole are possible if Einstein's theory is correct. And when finally black hole imaging was done few years ago, Roger Penrose got Nobel Prize in Physics just 2 or 3 years ago, I think. So that was also a prediction made by Einstein. And one of that prediction was that gravitational waves exist. So what do we need to know about general theory of relativity? We need to know a few things. That space-time curvature gets affected by gravity first. That is, around massive object, time slows down. We can remember it like this. We also can remember that this theory also predicts that universe is expanding. This theory also predicts that black holes can exist. This theory also predicts that gravitational waves are a possibility. Now what are gravitational wave? Coming to the topic which is given in your material. So when we think of waves, we think of some vibration. When we think of sound wave, then sound wave is vibration in air. That air particles are coming closer together and then being compressed and stretched all the time. Whenever they are compressed, the pressure increases. Whenever they are stretched, the pressure decreases. So sound wave is nothing but a pressure wave. So air pressure hai, that is continuously dropping, increasing, dropping, increasing, and somehow that can be that can produce an electric signal, and that electric signal our brain can make sense of it, and we get to talk to each other using sound wave. So sound wave is basically falling and dropping air pressure. If you do not have any air, then you do not have sound wave. You cannot speak in space. Other person will not be simply able to listen to you. Will only see the mouth moving. Electromagnetic wave, which what light is. Electromagnetic wave is vibration of electric and magnetic field, and because it is vibration of electric and magnetic field, it does not require a medium, and we know some of the properties. We know what will be its frequency or wavelength, or we know its speed, of course. We also know that how it can be produced, various type of electromagnetic waves, uska mechanism kya hoga production ka, we know all of those things. And remember that every electromagnetic wave is basically an information carrier. That is a very important point I'm making here. That every light is a carrier of information. Just for example, the fact that I can see you because of this prevailing light in the room which gets reflected by you. It falls on my eyes, all of those photons falling on my eye, and my brain then is able to convert that into electrical signal and is able to see you. Or the fact that I can see this light because it literally is emitting light here. So either it is reflected, emitted, scattered, refracted, whatever. But light is a carrier of information, and the object it has interacted with, either by reflection or refraction or scattering or emission or absorption, all of that tells me about that particular object. Jaise I get to see the color and the shape, everything for all of you, right? So that is why I made that statement that light, every type of light is an information carrier. Even X-ray is an information carrier. Remember, this is only visible light we are talking about. But as I said earlier, light can be X-ray, it can be gamma ray, it can be infrared, it can be UV, it can be radio wave, microwave also. And all of that is carrier of information. But now I have one more carrier of information. That carrier of information is gravitational wave. So unlike electromagnetic wave, which basically is a vibration of electric and magnetic field, gravitational wave is vibration of space-time curvature itself. That there is so much of energy. By the way, one of the consequences of Einstein's special theory was that mass and energy are not separate from each other. E is equal to mc squared, jo hum padhte hain, that is a consequence of special theory of relativity. That mass and energy, they can be converted into each other. So when Einstein gave general theory of relativity, and when he talked about gravitational wave, then essentially he's saying that there can be vibrations in space-time if there is a massive energy event, massive objects colliding with each other, producing a lot of energy, and that energy is going to now create vibration in space-time itself, and that is what gravitational waves are. That gravitational waves are vibration in space-time which travels with speed of light, which can be calculated. But there, ये क्या कर रहे हो आप? आप दूर से करो जरा. So जो gravitational wave जो है, that is a vibration of space-time, which can, again you are this is disturbance. So gravitational wave is vibration of space-time which travels with speed of light, and that can happen even when sun accelerates, by the way. As sun moves, even that is causing a gravitational wave. The only thing is that this gravitational wave will be so weak that you do not get to detect it. But if you have an event of cataclysmic scale, if you have an event which is going to produce so much of energy that we cannot even imagine it, that when think of two black holes colliding with each other, or a black hole merging with a neutron star, or a very heavy star undergoing supernova, when such things happen, it produces so much of energy that now this gravitational wave, even if it is very far away and very old, as it travels across space-time, we can feel it. Now we cannot feel it, but we can make detectors which can feel it. So gravitational wave exists, that was theorized by Einstein about 100 years ago. And finally, for the first gravitational wave which was detected, that happened in 2015, almost more than 90 years after its prediction. And the prediction was done by a setup called LIGO. Literally, you have this setup, LIGO. I'm not going to explain the working of the LIGO. I will briefly mention it, that LIGO is this two L-shaped interferometer. You have basically a mirror here. You have a source of light, a mirror. That mirror converts light into two parts. In 50, exactly whatever light is getting produced, it becomes two beam of light. And then you have a mirror here also, you have a mirror here also, and that mirror reflects that light back to the same place. Now, because the two distances are exactly same, the light is going to reach exactly at the same time, and this two light is going to interfere. Unless the length of these two objects can change. By some mechanism, what if the length of these two L-shaped devices, it gets to change. And that is what gravitational waves do. Remember, gravitational waves are vibration in space-time. They literally compress and stretch space. If a gravitational wave is passing by, then it is literally making space compressed and space stretched. No longer I'm talking about air or electric field or magnetic field. I'm saying that space in itself is getting compressed and stretched, and everything which is part of that space, that is also getting compressed and stretched. So as gravitational wave, for example, passes through us, then we get squeezed and stretched. The only thing is that this happens in nanometer, which we do not feel it. But this device can feel it. This device can detect even if that length has disturbed a little bit. And this device is called LIGO, Laser Interferometer Gravitational Wave Observatory. For the first time, it detected gravitational wave. But there were 3 such detectors, that just in case did not occur because of earthquake, did not occur because of some other thing. So we placed 3 detectors at 3 different places, 2 in US itself, 1 in Italy called Virgo. There is another detector called Virgo in Italy. And all 3 of them mentioned the same thing, that it is exactly same. The entire place witnessed the same gravitational wave. That was the first proof that gravitational waves no longer are just theoretical, they actually do exist. Now, why this topic is covered in your newspaper, in your magazine? 2 things. The first and more important, according to me, is this project called LIGO India project, that Government of India has collaborated with LIGO project, and 2 departments, Department of Atomic Energy and Department of Science and Technology, they have been given a lot of money by Government of India. And we are going to have one more observatory now in Maharashtra, in Hingola district, Maharashtra. We are going to set up an observatory, and we are simply going to call LIGO India. So this will be one of the gravitational wave observatories in a series of many such observatories all across the world. So India will actively participate in this discovery. And remember, I told you that how gravitational wave is an information carrier. So think about some cataclysmic events where black holes are colliding. We do not get any light from that, but we get gravitational waves. And by detecting gravitational waves, we can know about those events. We can know about that a neutron star merged with a black hole, or a star underwent supernova, or 2 black holes collided with each other. So now we have one more method to know about universe and the mystery it contains. So that is what gravitational wave observatory is all about. And the last thing, why this was in news, one more reason why it was in news, that if universe contained very heavy galaxies and stars, particularly in early days, early ka matlab yahan pe I'm talking about first 5-6 billion years, compared to 13.8 billion year, that is universe age as of now. So in the first 5-6 billion years, whatever black holes collided, and there have been much more collisions perhaps, and those gravitational waves still might be there. The only thing is that they have weakened a lot. And how do we know? And by the way, such gravitational waves are called low frequency gravitational wave, that inka energy itna kam hai, inka frequency itna kam hai, that even LIGO cannot detect it. LIGO can detect a more recent phenomena. More recent ka matlab jo last kuch maan lo million years mein hua ho. But it cannot detect something which is 5, 6, 7 billion years old. So how do we know about this pervasive gravitational wave of the primordial universe? Primordial ka matlab earlier universe. And that is where scientists have done quite a, again, this was theoretically always, people have always believed that low frequency gravitational wave exists. But nobody found it until last to last year. Last to last year there was a very important news that collecting data from many telescopes all across the world, scientists found some changes in the pulsar emitted by neutron star. So that is also something we should know. That when very heavy stars undergo supernova, very heavy ka matlab many times, 3 times, 4 times massive than mass of sun. When these heavy stars undergo supernova, they can become a neutron star or a black hole. A neutron star is second most dense object in the universe, just after black hole. And a neutron star is so dense that electrons enter inside nucleus, they react with proton, and proton, electron, they charge, cancel each other out charge, and the remaining material is mostly made of neutron. So I have literally something which is made of only neutron, hence the name neutron star. A neutron star can be very small, it can be smaller than Earth also, right, in terms of size, but in terms of mass, it can be 5 times massive than sun. So smaller than Earth, but 3, 4, 5 times massive than sun. That is the type of density I'm talking about. And smaller the neutron star, the more faster it is going to rotate on its axis. And as it rotates on its axis, it emitted pulses. Those pulses of energy, we call it pulsar. And pulsar का जो frequency है और जो pulsar का जो time है as we receive on earth, it is quite fixed. मतलब इसका जो time difference है, जो duration है, ये बहुत fixed है. And that is why neutron stars are often called cosmic clocks. That a cosmic phenomena is telling us about exact time difference. But the hypothesis was that pulsar data mein there should be some discrepancy, because if that pulsar, which whatever we have collected in last 30, 40 years, all the data which we have collected, that data must have interacted with, that pulsar must have interacted with that squeezing and stretching space because of gravitational wave, and we should see that error into it. So, or whatever is an error, it actually is because of the interaction with gravitational wave. And a group of few hundred scientists, they looked all of the data of the major telescope, the data which has been collected for last 30, 40 years, and they found precisely this, that whatever the theory is predicting, that by how much this pulsar data should show some departure, if there is gravitational wave, they found this, and there was an announcement that this entire theory, that there was a primordial, or there are primordial gravitational waves from early universe, which is all pervasive in the universe. We get to see that with the help of the data collected by telescopes, and particularly data collected of neutron stars. We call them cosmic clocks. So this is why also this was in news, that another hypothesis was proven to be true. The first hypothesis was that gravitational waves exist, which is proven to be true. And the second hypothesis is that even within gravitational wave, I can have two division, high frequency and low frequency. High frequency we know, but low frequency we did not know. And now we know that even low frequency gravitational waves can exist. You only need to remember a few things here. That if I have to ask 3 most important points about gravitational wave, then what will be those 3 points? Again, one by one, you can raise your hand and tell that all of whatever I have discussed, if you have to pick 3 points, then what it will be? Yes, go ahead. नहीं, उनको देना, उनको माइक देना.
Sir, why are gravitational waves not easily detectable?
Answer my question. Okay. Whatever we have discussed, tell me 3 things, 3 important things which you received, whatever I discussed. Forget about the question. First answer my question. I will answer your question also. You first answer my question.
No, sir, I have understood what you have told.
Okay, ठीक है. I want somebody else. Yes, go ahead.
Sir, it carries information.
Okay. What type of information? Be more precise. It carries information about cataclysmic events. Cataclysmic events such as merger of black holes or merger of black hole and neutron star or supernova, things like that. So it carries information about events which produce huge amount of energy. Cataclysmic scale, we cannot even imagine it. इस तरीके से आप समझो, ठीक है?
So second point is gravitational waves are vibration in space-time.
Okay, that's very good.
That's it, sir.
Few more things. I will add 2 more points. Okay, go ahead.
Sir, first point है, so nothing can travel with more than speed of light.
That is Einstein's special theory of relativity.
Okay, sir. So length, time can be contracted and dilated.
Okay. Again, still Einstein's special theory of relativity.
Sir, and third point है, so due to cataclysmic event, gravitational waves are produced and so because some of the changes in the pulsar emitted by the neutron star, there is a high probability that the that black hole exists.
Okay, ठीक है. Anyone else would add? I will make a small table of the quick summary of each and everything which I have discussed, and just remember that small table, that should be enough. So for example, the first thing is that जो special theory of relativity है, it fundamentally is based on a very simple but very powerful concept that speed of light that is the fundamental of special theory of relativity. That speed of light, no matter in which frame of reference you measure, it is going to remain the same. And a consequence of this is that it is a barrier. Nothing can travel faster than speed of light. Massless objects. I can give example of photon, which is basically light particle, can travel with speed of light. Only massless objects. So for example, an electron cannot travel with speed of light, a proton cannot travel with speed of light. Any object which has mass cannot travel with speed of light, and in fact nothing, even photon cannot cross this barrier here. Space-time are not different. We live in a 4-dimensional universe where there are 3 spatial dimension and 1 time dimension. We can witness length contraction. That same length, but 2 different measurement by 2 different observers. And time dilation, same event, but 2 different observers not agreeing on in what time frame this particular event happened. That is possible. Last but not the least, that energy and mass, they are not separate from each other. Energy and mass have a relationship which can be written as E is equal to mc squared. This is the mechanism behind nuclear energy, चाहे fission हो, चाहे fusion हो. That is what Einstein said in special theory of relativity. General theory of relativity. The most basic aspect of general theory of relativity is that जो space time curvature है is affected by massive objects which leads to gravity. What we witness, an attractive force, is an effect of curvature of space-time. So gravities are not a force in Einstein's general theory of relativity. It is a consequence of curvature of space-time. This theory also tells you that universe is expanding. This theory also tells you black holes can exist. This theory also tells you that gravitational waves can exist. And now the sub-bullet points of gravitational wave. Gravitational wave is nothing but a wave in space-time traveling with speed of light, which basically means that as it travels, it is going to squeeze and stretch space-time fabric. Second, a result of cataclysmic का मतलब very high energy producing events, result of cataclysmic events such as merger of black holes, supernova, neutron star merging with a black hole. Now ask your question. What was your question? आपने question था? Ask that. Okay, now that's a good question. Think about it. That why, how many stars are there in the sky? Can you take a guess? Not millions, like trillions to trillions. There are about 2 trillion galaxies. And there are, in every galaxy, there are about 400 to 500 million stars. The object which we see with our naked eyes, which we can see with our naked eyes, and the farthest object, is one collection of stars together, but we are not going to see the star. We are going to see a very dim light, extended light, and only at certain pockets of Earth, that is Andromeda galaxy, bigger galaxy than Milky Way. Whatever stars we see, those are stars of Milky Way galaxy. The stars of Andromeda galaxy, which is the nearest galaxy to Milky Way galaxy, we cannot see those stars individually with our naked eye. We can see that one fuzzy light, not from here. Delhi mein to star bhi nahi dikhte. But go to Ladakh and you see that one fuzzy light, take a telescope, you get to see that, okay, that is in itself in sky, there is another source of light coming, and that is Andromeda galaxy. That's it. You cannot see any other galaxy with your naked eye. Why you cannot see? Because the light coming from distant galaxies are so dim that your eyes cannot resolve it. हमारे eyes जो हैं इतने बढ़िया optical instruments हैं ही नहीं कि बहुत दूर के object को देख सकते हैं. So similarly, why gravitational waves are difficult to detect? That even if something happened which produced lot of energy, but it happened really in past, and overall those waves as they have traveled and as the time has been spent, that energy has gotten depleted. So that is why this energy is so less that detecting them will require special equipment such as what LIGO is. So the reason is quite simple, that the same way electromagnetic wave weakens, even a gravitational wave weakens, and a very weak gravitational wave will be very difficult to detect. Does that answer your question? Okay. Anyways, so a result of cataclysmic events such as merger of black holes, supernova, detected first by LIGO. This is laser interferometer gravitational wave observatory It is an L-shaped device. At this L-shaped device, you have mirror here, you have mirror here, and you have mirror here. And the goal here is that as light from this mirror and this mirror comes back at this point, it is going to interfere and it is going to lead to an interference pattern. And as long as this length remains the same, we know what type of interference pattern will be. But what if the length changes? And that length can change because of vibration. And one of the cause of that vibration can be gravitational wave. And this is exactly what LIGO did few years ago. And as of now, we also have LIGO India, which is proposed. In Hingoli, Maharashtra. And there are two more upcoming projects which are very famous. The first is a project called eLISA, Evolved LISA, and the second is a project called Einstein Telescope. Again, they both aim to detect gravitational wave. This much information, I think, should be more than enough for UPSC Prelims examination if UPSC picks up this theme. They have picked up this theme at least twice or thrice in past. जैसे, one of the topic they had asked in past was about Evolved LISA. That Evolved LISA is a proposed setup by European Space Agency with collaboration from NASA. यहाँ पे goal ये है that 3 such mirrors they are going to launch into space, millions of kilometers away from Earth. And these 3 mirrors, they are going to revolve around Sun now. And these 3 mirrors all the time they are going to make an equilateral triangle shape. But equilateral triangle का जो एक side होगा, that will be about 2-3 million kilometers. The UPSC, how it asked the question, it gave a statement that a scientific mission has been proposed which will include 3 flying objects forming a triangular formation with side of one triangle being 1.5 million kilometers. And which of the project is being described in the above paragraph? The answer was Evolved LISA. They did not ask that it is trying to detect gravitational wave. But you should know that yes, it is trying to detect gravitational wave. And there is one more proposed mission, Einstein Telescope, that will be under underground gravitational wave observatory. So I think this much information is more than enough for prelims examination. And I have my again own doubts that such type of complex theme, UPSC does not go into a lot of complexity. They can pick this theme, but the questions will be very simple and very straightforward. I keep repeating this. If you have any question, you can go ahead and ask. Yes.
So one point, जैसे आपने पहले ही बोला कि स्पीड ऑफ लाइट इज सेम इन ऑल इनर्शियल फ्रेम, यहीं पे थोड़ी सी कन्फ्यूजन हो गई. जैसे हमने 10th क्लास में पढ़ा था कि मीडियम के ऊपर स्पीड ऑफ लाइट डिपेंड करती है, लाइक वैक्यूम में डिफरेंट होती है.
ओके, ठीक है.
जैसे रिफ्लेक्टिविटी चेंज होता जाता है वैसे लाइट चेंज करनी जाती है. तो सर ये पॉइंट मुझे दोनों में ऐसे
दोनों बिल्कुल ही अलग कॉन्सेप्ट है. तो क्वेश्चन ये है, आई होप कि क्वेश्चन समझ में आ गया होगा, दैट स्पीड ऑफ लाइट हमने एक चीज़ क्या पढ़ रखा है, दैट स्पीड ऑफ लाइट इन अ मीडियम डिक्रीजेस. उसका कारण ऑल टुगेदर डिफरेंट है. दैट लिक्विड और सॉलिड ऑब्जेक्ट्स दे कॉज सम सॉर्ट ऑफ बैरियर टू द प्रोपेगेशन ऑफ इलेक्ट्रोमैग्नेटिक वेव. जो उनके अंदर जो एटम्स एंड इलेक्ट्रॉन्स हैं, दे डू नॉट अलाउ लाइट टू एज स्मूथली पास एज इट कैन इन वैक्यूम. एंड बिकॉज ऑफ दैट द स्पीड डिक्रीजेस, डज नॉट इंक्रीज, it can only and only decrease. So in vacuum, if it is traveling with 3 lakh km per second, it is going to decrease even in atmosphere, but that decrease is negligible. In water, it becomes very much noticeable that speed has decreased, and in glass it has further decreased. That has to do with the nature of electromagnetic wave, and remember, after all, since it is electromagnetic wave, it interacts with the atoms and molecules of a medium. And those atoms and molecules, if you want to imagine it, aise samajh lo, that they cause some sort of barrier. And what you study as refractive index, padha hai na aapne refractive index, you can think of that as the consequence of, a cumulative consequence of that particular barrier, the speed decreases. Nothing to do with the concept of space-time which we are discussing here. Okay? पीछे वहाँ पे.
सर आपने बताया था कि जितना भी मासिव ऑब्जेक्ट होगा उसकी ग्रेविटी की वजह से स्पेस टाइम कर्वेचर जो इफेक्ट होगा, तो मतलब सर जितना मासिव ऑब्जेक्ट है वहाँ पर टाइम स्लो होगा, वो सर क्यों होगा? इसलिए क्यों लाइट वहाँ पर मतलब स्लो हो जाएगी उसकी ग्रेविटी की वजह से ऑब्जेक्ट की, या कोई और रीज़न है?
ओके, क्यों होगा? क्योंकि जो स्पेस टाइम ज्योमेट्री है, जैसे फॉर एग्जांपल मेरा पूरा अब यही वी हैव टू गो इनटू देन टेक्निकलिटी, कि अभी तक जो आपने ज्योमेट्री पढ़ रखा है, you have studied geometry in your 9th, 10th, 11th, 12th classes. Whatever geometry you have studied, that is called Euclidean geometry. Euclidean geometry does not deal with curvature of space-time. First, we start with this fact that there can be curvature in space-time. That is the first thing. Once we start with this fact, then you can mathematically show that why massive objects will compress the space-time fabric around it. And what you think of a time gap, right? The time gap is not same around this object compared to some other object. To actually appreciate it, we have to go into the mathematics part of it, but we do not have to do that. Right? Any other question? Yes.
Sir, is there any specific criteria why this particular location has been chosen as LIGO?
I'm not very sure about that, but if the question is that why this particular location, Hingoli ki baat aap kar rahe, why it has been chosen, I think the first and the most important criteria, of course, will be that this land was available, and there was no, as such, it was not, I hope that it was not cultivable land, not being used for any particular specific purpose, not being disturbed by a lot of construction activity in the area. So I will have to assume that this land was relatively unused at this point of time, either for agriculture or industrial purposes. And that is why acquisition was also simple, and because not lot of activities going on, they are not going to have any type of consequence on the experimental outcome. Right? I will assume that maybe this was the reason. Any other question? Anybody has? Let's complete few more topics which is associated with this. I will just extend this class by 10-15 more minutes, don't worry. I was hoping to complete space technology in today's class. We have come only halfway, I guess. Few things about black holes we should know about. Black holes are a region of space-time where the gravity is so intense, or the space-time curvature is so much curved that even light cannot escape. And आप इसको ऐसे समझ लो कि जितना massive object होगा, उतना ज़्यादा escape velocity होगा. जैसे Earth पे escape velocity is 11.6 kilometer, 11.2 kilometer per second. On Sun it will be much more higher, of course. But imagine a place where the escape velocity becomes more than 3 lakh kilometer per second. That is what a black hole is, that nothing can escape. Even light cannot escape, and since nothing can travel faster than speed of light, then even light cannot escape. And such areas are called black holes. Black holes have a region around them. That region is called event horizon. And anything which is part of event horizon or becomes part of event horizon, there is a 0 probability that it is going to escape. So anything which is, so for example, if I have a black hole and it has an event horizon around it, then anything which is part of that event horizon is not going to cross that event horizon. It is going to fall directly into black hole. That is the second thing. And again, as I said, it is a direct consequence of Einstein's general theory of relativity. We do not understand a lot about black hole because theoretically Einstein theory tells us that black hole ka jo center hai, which is by the way is called singularity, and that center of black hole, you have all of that mass concentrated in 0 volume, which basically will make density infinite. Now infinite looks good in mathematics, but in physics nobody believes in infinite or infinity. Or saying that infinity exists at one point, that does not make sense. So that is why black hole ka jo center hai particularly, which is called singularity, there is a word for it, and that singularity is considered to be as of now non-explainable. We cannot explain the center of the black hole. Black holes ke around you can find lot of particles swirling around it, and because black hole has a very powerful gravitational pull, those particles accelerate more and more, and if they accelerate more and more, they are going to emit more and more energy, and if they are beyond event horizon, that energy we can record. And that is exactly what we did when few years ago there was a news that a project called Event Horizon Telescope project, which released image of first a black hole, not part of our galaxy, but another galaxy. That black hole was called Miser 87. And now, few years ago, another image was released, which is at the center of Milky Way galaxy. That black hole is called Sagittarius A. So again, we should know these two words, M87 and Sagittarius A. These are the two black holes, name of black holes which are given, found at the center of two galaxies. So the prevailing theory is that every galaxy at its center has a supermassive black hole which is billion times more massive than Sun. In contrast, when a very heavy stars die, as I told you earlier, that when heavy stars die, not Sun, when Sun is going to die, it is finally going to become a white dwarf star. But a star much heavier than Sun, in fact it was an Indian origin scientist who theorized this, Dr. Chandrasekhar. And Dr. Chandrasekhar mathematically showed that if a star is 1.4 times heavier than Sun, then that white dwarf is not going to be stable. It is going to further collapse and it can become either a neutron star or a black hole. That, by the way, that limit is called Chandrasekhar limit. Chandrasekhar limit has to do with that up to what mass a star remains stable and does not undergo supernova. If it is more massive than this limit, then star is undergoing supernova explosion. After supernova explosion, as I said, there are two possibilities, neutron star, and the second possibility is a black hole. That black hole is called stellar black hole. And within Milky Way galaxy itself, there can be millions of stellar black holes. But in every galaxy at its center, you have a supermassive black hole. That will be only one. Some of the supermassive black holes, they are so far away from all the stars that they are not very active. They do not eat the nearby stars. But there are certain black holes which are so huge, which have become so humongous, that they are literally engulfing stars in the nearby region. And there are the most powerful black hole which scientists know about. It eats one star a day. In one day, it finishes off an entire star. It is so humongous and so large and so massive. So when such type of black holes, when they are feeding upon the nearby star, as the stellar material comes, all of that stellar material comes towards black hole, it produces so much of energy that this energy we can see. And such type of supermassive black hole found at the center of galaxy is called active galactic nuclei. Active in the sense that this black hole is not passive. This black hole is literally feeding upon the nearby material. And such type of active galactic nuclei, ये जो पूरा जो भी object है, whatever this object is basically a supermassive black hole, but a supermassive black hole which is feeding upon all of the nearby material. All of that together, this is the brightest event in the universe. That is called quasar. So quasar is 1,000 times brighter than supernova. And one supernova is so bright that it can outshine an entire galaxy. Think about it. A supernova is a star which is collapsing, and it is such a bright event that it can become brighter than the entire galaxy together. We're talking about so much of energy, but a quasar is 100 and 1,000 times brighter than supernova. So quasar is nothing but an active galactic nuclei which is powered by a supermassive black hole. Quasar oriented in random direction, we can call it quasar, but a very particular type of quasar which is oriented towards Earth, and which from time to time it is going to release that energy and we can record that energy, that is called blazar. So blazar is a specific type of quasar which is oriented towards Earth, or in any case oriented towards a particular object. So ये जो दो words हैं, blazar and quasar, remember that these are called active galactic nuclei which are powered by supermassive black holes. What are supermassive black holes? These are black holes found at the center of galaxy, and they are so heavy that the same way planets revolve around sun, all of the stars revolve around the center of the galaxy. So hence the concept of supermassive black hole and the fact that all the stars revolve around center of galaxy. These are some of the words you have to know. Yahan pe the most difficult type of question I expect here is that these terms will be thrown to you and you are supposed to know what do these terms mean. And even if you know the meaning of these terms in 1 or 2 lines, that will be more than enough to answer questions in prelims. Again, only important for prelims examination. If you have any doubt here, you can ask question. A quasar is oriented, for example, so blazar is if it is oriented towards Earth, that if majority of that energy, or if when we look at particular event, I can look at particular event from multiple perspective. I can look it from an oblique perspective, but I can look it from a direct perspective. So think of an event, think of this bottle's orientation, and think that this is my point of view. So think of this bottle's orientation as a quasar. If it is orientation like that, I can simply call it quasar. But if it is pointed towards my point of view, I call it blazar. So again, even a blazar is an active galactic nuclei. The only difference is that iska jo orientation hai, that is towards Earth. Nothing. इससे ज़्यादा और कुछ भी difference जानने की ज़रूरत नहीं है. Any other question if you have? And one last thing I want to discuss is something called gravitational lensing, and we will complete this topic of Einstein's theory of relativity or by the way, you can add one more thing. जब हम discuss कर रहे थे consequences of general theory of relativity, then we can add one more thing here, gravitational lensing. Gravitational lensing is again now very simple to understand once we appreciate Einstein's theory of relativity. That we all have done this experiment as a child. We took a convex lens and we converged the solar light and we have burnt a paper. I'm very sure that most of you or all of you have done it. So because of prevailing light, this paper is not going to burn. But if I converge all of that light, all of that energy at one point, then it is going to start burning. So what lens does, lens converges light which is going in different direction, it is going to converge that at one particular point. That is what a convex lens or a concave mirror can do. We have studied that in our 9th and 10th class optics. In astronomy, there is a phenomena called gravitational lensing. It's a very powerful phenomena and very useful for astronomers. Imagine a very distant galaxy or a very distant event which is producing light, but as I said earlier, the farther away the things are, the light is going to become much more dim. The light is so dim that even with the most powerful telescopes, we do not get to see a very clear image of that, right? Our eyes clearly cannot see, but even with most powerful telescope, turns out that we cannot see things very properly. Unless, as it turns out, that this light as it was traveling, in its path towards Earth, you had a galaxy or even a cluster of galaxy, many galaxies together. And because of that, there is now a curvature of space-time. And remember, light travels in straight line, but what if space in itself is curved? So if space in itself is curved, that light will seem to be bent. हमने अभी तक यही पढ़ा ना कि light travels in a straight line. But straight line तो तभी होगा ना अगर space straight हो. अगर space-time खुद में bend हो, so that light is also going to bend. And जितना massive object होगा, light is going to bend even more and more. So light which would have scattered here and there, and the amount of light which we would have received, it's so dim that we would not have made sense at all what that particular object is. But thankfully for our benefit, you had a galaxy or a cluster of galaxies. Because of that, light got converged. And now I have a telescope here, powerful enough, that it can collect that converged light and it can see that very distant galaxy, even though it is very far away. So it is producing a very similar thing, like what a lens does, how a lens converges light. Here also light is converging, but not because of lens, but because of gravity. And gravity of very massive object. And this can be very useful in astronomical observation, and all of the telescopes which we do have, they do rely upon this phenomena of gravitational lensing. And that is how we get to know about distant stars and distant galaxies, which may be millions or billions of light years away from us. So even gravitational lensing jo hai, that is also a consequence of Einstein's theory of relativity. And because light is getting distorted, and all of that light is same object ka image jo hai, light jo pura distort ho rakha hai, so often we can find a distorted image of same object. Ek hi object hai, but I can find its distorted image in various form. I can find an image like a cross, which is called Einstein cross, or I can find an image like a ring, which is called Einstein ring. So Einstein cross and Einstein ring occurs fundamentally because of gravitational lensing. That it is a lens, but it is not a very good lens. Lens क्या करता है, सारे light को एक point पे converge करता है. So it is a lens, it is converging, but it is converging at multiple points. And all of those multiple points where this light is converging, all of them is an image. And that is how you get a ring shape, or that is how you get a cross shape. But nonetheless, it is quite useful in astronomical observation. So only two things here, that gravitational lensing, what it is simply convergence of light because of presence of heavier object, which can be a galaxy or a cluster of galaxy. This allows you to see even a farther object, much distant object, जिसका light इतना dim हो जाता, अर्थ तक पहुँचते पहुँचते, that we would not have seen it. But because of this convergence, we get to see it. And why that light is bending, why that light is converging? Because of Einstein's general theory of relativity, which tells us that because of heavier object, space-time can have a curvature, and then even light can bend and light can converge. It is not going to move in straight line. So this is also something we should know, only two things. What is gravitational lensing and what does it do? That's it. And if you know these two things, I think you can solve questions in prelims examination. We will continue this discussion in the next class. Hopefully we will get to complete this topic of space, and we will start information and communication technology. Sorry, कुछ और questions हैं? हाँ जी.
So does James Webb Telescope work on this gravitational lensing?
It does, not gravitational wave, but lensing.
Yes, sir.
So many of the images of Webb telescope which you have seen, particularly Webb telescope can work in multiple ways. Just 1 minute, guys. Webb telescope, sometimes it focuses on a very specific object, but sometimes it collects light from the entire sky and all the objects which are in the entire sky. And in such cases, many of those images which you see, there is a very good chance that they are a result of gravitational lensing. So answer is yes. Any other question? I will see you guys in the next class.